Here's something worth turning over as you settle in tonight. Right now, lying there in the dark, your body is being held down by a curve you cannot see, the gentle curve of the earth, pulling everything toward its center. Every point on your skin sits at a very slightly different angle to that center than the point right beside it. You are, in this exact moment, a shape, a complicated one made of countless smaller shapes, resting inside the shape of the room around you, the shape of the walls, the shape of the corners where those walls quietly meet the ceiling above you. Everything you can feel right now, even with your eyes closed, is geometry. It always has been. You've just never had a reason to think of it that way before. Tonight we're going to move slowly through the story of geometry, from its very beginning, the earliest people who needed to measure the world they lived in, all the way through to some of the stranger, softer ideas about shape that came much later. We'll talk about farmers straightening out flooded fields with nothing but a length of rope. We'll talk about scribes pressing numbers into wet clay on the banks of two rivers far from Egypt. We'll talk about a city built on a grid so precise that the bricks still fit together the same way, thousands of years later. None of this needs to be remembered. None of this is being asked of you. You're simply here to listen, and to let your body get heavier, and to let your mind loosen its grip a little at a time. If you drift off somewhere in the next few minutes, that's exactly what this is for. There's no test waiting for you tomorrow morning. There's no version of tonight where you did it wrong. If your eyes are already heavy, let them close all the way, and let my voice keep going without you. Everything I say will still be true whether you're awake to hear it or asleep beside it. For now, there's nothing to do but breathe, slowly, and let this settle over you the way warm water settles into the shape of whatever it's poured into. Let's go back a long way, further back than most people expect when they hear the word geometry. Before Greece, before the names you might remember faintly from a school classroom, we're going back almost 4,000 years, to the river valleys of ancient Egypt and to the land between two rivers that we now call Mesopotamia. That's where this whole story quietly begins. Not with clever ideas or abstract thinking, but with mud and rope and the ordinary yearly problem of figuring out whose land was whose. Picture the Nile River in Egypt, somewhere around 3,000 years before our own time. Every year, without fail, the river would rise and spread out over the land. This wasn't feared the way we might picture a flood today. It was expected. It was even welcomed, because the water carried a rich, dark soil down from higher ground and left it behind across the farmland along the riverbanks. The land became fertile again, ready for another season of crops. The ancient Egyptians actually named their own country after this dark soil, calling it the Black Land, in honor of what the flood left behind each year. But tucked inside this yearly gift was a yearly problem. When the water pulled back, it didn't just leave rich soil behind. It also swept away anything that had marked where one farmer's land ended and the next one began. Stakes, stones, small fences, all of it gone, carried off by the current or buried under a fresh layer of silt. So every single year, once the water receded, someone had to go back out into the fields and work out, all over again, who owned what. This wasn't a small or casual task. Egyptian farmers were taxed according to how much land they held, so if the boundaries were unclear, or if a plot had quietly shrunk because of the flooding, that had real consequences for a family's food and for what they owed the state. The people who did this yearly work of remeasuring were later given a name by Greek writers, a name that translates loosely to rope stretchers, and that name describes exactly what they did. They were surveyors who worked with long ropes, knotted at even intervals, stretched tightly across the land to remeasure and remark the boundaries after every flood had passed through. Here's where it becomes something more than a clever workaround, because that rope wasn't just useful for measuring distance. It was also a tool for creating one very particular and very useful shape, a right angle, a perfect square corner, the kind the Egyptians needed constantly, for fields, for homes, and for the enormous stone monuments being raised during this same stretch of time. If you take a rope and tie knots along its length so that it's divided into 12 equal sections, and then you pull it taut into a triangle with one side made of 3 sections, one side made of 4 sections, and the last side made of 5 sections, something quietly reliable happens every time. The angle where the 3-section side meets the 4-section side is always, exactly, a right angle. Not close to one, not usually one. Always, every single time you try it. The Egyptians didn't necessarily understand why this worked. That deeper understanding was still centuries away, and we'll come back to it a little later tonight. But they knew, through patient repetition, that it did work, and they leaned on it constantly, to square off fields, to lay the foundations of temples, and to align the corners of the pyramids at Giza, structures being built during roughly this same period, with corners so precise that people who study them today are still quietly struck by how accurate they are, off by only the smallest possible fraction across an enormous base of stone. I want you to hold onto this rope and its simple triangle gently for now, the way you might hold onto the last thought before sleep, because we'll return to it later in a fuller, more complete form. For the moment, just notice this one thing. The Egyptians had found a pattern hidden inside the physical world, a relationship between certain lengths of rope and a certain angle, purely through trial and repetition, without yet having any language to explain why that pattern existed at all. They knew the what. The why would come later, and it would come from somewhere else entirely. Around this same broad stretch of time, in Mesopotamia, in the land between the Tigris and Euphrates rivers, in what is now Iraq, another civilization was working through very similar problems, though with a flavor that leaned even more toward pure calculation. The people there, the Babylonians, left behind thousands of clay tablets, pressed with wedge-shaped writing while the clay was still soft and workable. A good number of these tablets are, in essence, geometry problems, along with their solutions, carefully worked out by scribes. One tablet in particular, now kept far from its original home and known today by a modern collector's name, contains a long table of numbers. Many people who study ancient mathematics believe this table represents sets of 3 whole numbers that behave the same way as that Egyptian rope triangle. 3 numbers that fit together to form a right angle, but scaled up into much larger and more varied combinations. This suggests the Babylonians had worked out a systematic way of generating these number sets, nearly 1,000 years before the Greek thinker most people associate with this kind of triangle was even born. The Babylonians also worked out ways to measure the area of fields, shaped like trapezoids, 4-sided shapes with 2 sides that lean toward each other, and they had their own working approximation for the relationship between a circle's edge and its width across, a number close to what we now call pi, though not quite as accurate as what would come along much later. Their number system was built around groups of 60 rather than groups of 10, and this is actually the quiet reason we still divide a full circle into 360 degrees today, and why we still divide a single hour into 60 minutes. That's not some modern arbitrary choice made recently. That's a 4,000-year-old habit, still living quietly inside every clock face and every compass, whether anyone using them today knows it or not. What matters most about both of these early civilizations, the Egyptians along their river and the Babylonians between theirs, is that their geometry was entirely practical, entirely grounded in real, immediate need. It existed to solve problems people actually faced, taxing farmland fairly, keeping buildings standing, tracking the slow movement of stars and seasons for planting and for ceremony. Nobody standing in a field along the Nile was asking why the 3-4-5 rope triangle produced a perfect right angle every time. They were only asking whether it worked, and since it always did, they simply kept using it, year after year, generation after generation. Before we leave this ancient world and move toward Greece, there's one more early civilization worth resting on for a moment, because it's often quietly left out of this story, and it shouldn't be. Far to the east, in the Indus Valley, in what is now Pakistan and northwestern India, cities were being built around this same broad era with a level of careful planning that still holds up remarkably well when studied today. Streets in these cities were laid out in neat, precise grids, meeting each other at clean right angles, and the bricks used across the entire civilization followed the very same standard ratio of size, no matter how far apart two building sites happened to be. This tells us something gentle and important: the idea of a repeatable, dependable shape, one you could recreate exactly the same way every single time, wasn't something only one culture stumbled onto by chance. Several very different civilizations, separated by vast distances and with no contact between them, arrived at very similar solutions, because the physical world itself, gravity pulling down on every wall, water needing somewhere to drain, weight needing something stable to rest upon, kept quietly guiding human beings toward the same small set of dependable shapes. By the time we reach roughly 600 years before the more familiar Greek era most people picture when they hear the word geometry, human beings across several separate continents had already been using geometry, in this practical, hands-on way, for well over 2,000 years. They had built structures that would go on to survive more than 4,000 years. They had laid out entire cities on grids so exact, they still line up cleanly today. They had worked out how to tax land fairly, using nothing more than a knotted rope. And yet all of this careful, hard-won knowledge still existed as a loose collection of individual tricks, each one learned through repetition rather than through reasoning. There was, as yet, no thread tying it all together, no sense that these separate, useful facts were really just different faces of a smaller and deeper set of truths waiting underneath them. That quiet gap between knowing that something works and understanding why it has to work is where we'll rest next, before drifting further into the story still ahead tonight. Let's talk now about what was missing from all that early, practical knowledge, and why it mattered so much that someone, eventually, went looking for it. Picture yourself as a trader or a quiet thinker, somewhere around 2,600 years ago, in a city called Miletus, on the coast of what is now Turkey. You've heard about Egyptian geometry. Maybe you've even traveled there yourself and seen the pyramids, the temple corners, the fields squared off with knotted rope. You know the rope trick works, every time. But something about simply knowing that it works, without knowing why, has started to feel unsatisfying to you, especially if you're the kind of person who has begun asking bigger questions about the world. Questions like what everything is made of, and whether there's some deeper order underneath it all that a person could actually reach through careful thought, rather than just through watching and repeating. This is roughly the frame of mind of a man named Thales, who lived in that same coastal city, and who is often remembered as the first person in this part of the world to try to prove geometric facts rather than simply use them. We don't know a great deal about Thales as a person. Almost none of his own writing has survived the centuries between his life and ours. Most of what we know comes second-hand, from later writers describing his reputation and his work. But the story that keeps repeating across those later accounts is this. Thales traveled to Egypt, learned the practical methods the surveyors used there, and then did something quietly different with what he'd learned. Instead of simply applying the methods the way everyone before him had, he started asking why they worked, and he tried to show that they had to be true, using careful reasoning, rather than simply showing that they had happened to be true every time he'd personally checked. There's a story about Thales, and whether it's exactly true in every detail or not, it captures something real about this shift in thinking. The story goes that he worked out the height of the Great Pyramid by measuring the length of its shadow at the precise moment when his own shadow was exactly as long as he was tall. Think about that for a moment. If your own shadow matches your own height exactly, then in that same instant, the pyramid's shadow should match the pyramid's height exactly too, because the angle of the sun is the same for both of you at that moment, whether you're a person standing in the sand or a monument built centuries before you were born. It's a simple idea, almost embarrassingly simple once it's explained, but notice what's actually happening underneath it. Thales isn't just measuring a shadow, he's reasoning about a relationship, a ratio that holds steady, no matter how large or small the object casting the shadow happens to be. He's noticing something that isn't really about the pyramid at all, but about any object and its shadow, at that one particular moment of the day. This is the quiet beginning of something that Greek thinkers would spend the next several centuries developing into an entirely new kind of knowledge, something we now call geometric proof. The idea is this: you don't have to establish a fact about shapes by checking enough examples until you feel confident. You can instead start from a small number of things that are obviously true, and then reason your way forward, one careful step after another, to a conclusion that has to be true as a result. No exceptions, no room for doubt. This distinction is worth sitting with slowly, because it's really the difference between two very different kinds of confidence. If you check that a certain triangle always produces a certain angle 100 times in a row, you might feel very sure it always will. But you haven't actually proven that. Maybe the 101st time turns out differently. A proof removes that uncertainty completely. Once something has been proven, from true starting points, using only valid logical steps, there's no need to keep checking it again and again. It simply has to be true, every time, forever, whether anyone bothers to check it or not. After Thales, this new way of thinking about shape started drawing more followers, and one of the most important among them, and also one of the strangest, was a man named Pythagoras, who lived a little later, in the southern part of Italy. Pythagoras founded a kind of community there, part school, part religious circle, part research group, all blended together in a way that feels unusual to us now, but made complete sense within his particular view of the world. He and his followers believed that number itself was the fundamental substance underneath everything, that music, the movement of stars, the shape of physical objects, all of it could ultimately be understood through relationships between numbers and shapes. The idea most people still associate with his name today describes a relationship between the three sides of a right triangle, a triangle with one perfect square corner somewhere inside it, and remember that Egyptian rope triangle from earlier, the one with sides of 3, 4, and 5 knotted sections. What this idea does is explain, in a general and fully provable way, exactly why that triangle, and every other right triangle like it, behaves the way it does. Let me walk through it slowly, without any numbers or equations, because I want you to feel the shape of the idea, rather than just hear a rule recited. Take a right triangle, any right triangle at all. The two shorter sides that meet at the square corner are called the legs. The longest side, sitting across from that square corner, is called the hypotenuse. Now imagine building an actual square, a real physical square, out along each of these three sides, using each side as one edge of its own little square. What gets proven, through careful reasoning rather than through measuring, is that the area of the square sitting on the longest side is always, exactly, equal to the combined area of the two smaller squares put together. Always. For every right triangle that has ever existed, or ever will, in any size, at any proportion at all. Let me say that once more, a little differently, because ideas like this settle in more gently when they're allowed to repeat. If you have a right triangle, and you build a small square garden along each of its three edges, the largest garden, the one along the slanted longest side, holds exactly as much soil as the two smaller gardens combined. Not roughly the same, not usually the same, exactly the same every single time, without exception. Now think back to that Egyptian rope, with its sides of 3, 4, and 5 sections. 3 times 3 is 9, 4 times 4 is 16, 9 plus 16 comes to 25, and 5 times 5 is also 25. The numbers line up perfectly. This is exactly why that particular rope triangle produced a perfect right angle every single time the ancient surveyors used it along the Nile. Without knowing the deeper reason behind it, they had stumbled onto one specific example of a much larger and completely general truth, a truth that wouldn't be proven in the careful, reasoned way we've been describing for well over 1,000 years after those surveyors had already put it to use in their fields. This is the first real turning point of our night, the moment where a practical trick quietly becomes a proven universal law. From here, over the following couple of centuries, this new proof-based way of thinking about shape kept being refined, kept being carried forward by different thinkers scattered across the Greek world, until it eventually reached the person most people picture today when they hear the word geometry, even though, as you now know, he was really just one careful voice within a tradition that had already been growing for generations by the time he arrived. That person lived and worked in the great coastal city of Alexandria, in Egypt, gathering together everything that had come before him into a single collection of books that would go on to shape how geometry was taught for well over 2,000 years afterward, nearly unchanged, right up through the early parts of the last century, in classrooms scattered across much of the world. What made this collection so lasting wasn't that its author had invented every idea inside it. Many of the facts, including the relationship we just walked through with the right triangle, were already known before he began writing. What he did instead was something closer to architecture. He gathered the scattered, individually proven pieces of Greek geometric knowledge and arranged them into one unified structure, starting from a very small handful of basic starting points and building everything else outward from there, one careful step at a time, with nothing added along the way that hadn't already been earned through reasoning. He began with simple definitions, plain descriptions of the most basic objects imaginable. A point, he said, is something with no size at all, not small, not tiny, but genuinely without any size whatsoever, a pure location and nothing more. A line has length, but no width. These definitions sound almost like philosophy, and in a real sense they are, because they describe idealized things that don't actually exist anywhere in the physical world around you. You have never seen a true geometric point, and you never will, because any mark you could make, with a pencil, with anything at all, has some tiny width of its own. This geometry lives in a realm of pure abstraction, and that abstraction is exactly what gives it its quiet, dependable precision. After the definitions came a small handful of starting assumptions, statements simply accepted as true, without needing proof, because they seemed obviously reasonable on their own. A straight line can always be drawn between any 2 points. Any line segment can be stretched out indefinitely. All right angles are equal to one another. From these few plain assumptions, and from a handful of other very basic common notions, an entire enormous structure was built. Hundreds of separate results, each one resting only on what had already been established before it. Nothing assumed without reason, nothing smuggled in along the way. The whole towering structure resting, quietly and completely, on just a few carefully chosen footings, the way a very tall building might rest its full weight on a handful of foundation stones, set deep and sure into the ground. Not long after, in that same intellectual world centered around Alexandria, another figure carried this careful, reasoned approach even further, working out the relationships between spheres and the cylinders that contain them, calculating a close approximation for that constant relationship between a circle's width and its distance around, using nothing more than patient, careful reasoning about many-sided shapes drawn snugly inside and just outside a circle. And still another figure, working a little later, spent his efforts studying the family of curves you get by slicing through a cone at different angles, curves that seemed, at the time, like nothing more than an elegant curiosity, with no purpose beyond their own quiet beauty. It would take nearly 2,000 years before anyone realized those very same curves described the actual paths that planets trace as they circle the sun. Rest here a moment. None of these names or dates need to stay with you. What matters is only the shape of the story itself, patient minds, working slowly, turning practical tricks into permanent truths, one careful step following the last. After Euclid gathered together all of that early Greek reasoning into one connected structure, geometry did not simply stop and rest. It kept moving forward, kept being carried further, by other careful minds working in the centuries that followed. Most of them still gathered in that same great coastal city where Euclid himself had worked, a city that remained, for hundreds of years afterward, one of the true centers of learning in the ancient world. The most towering figure among these later thinkers lived a generation or two after Euclid, in the Greek city of Syracuse, on the island of Sicily, and his name was Archimedes. You may already know a small piece of the story that's often told about him, the tale of him stepping into a bath, noticing the water rise around him, and running out into the street, still dripping, shouting a single word that meant something like, "I have found it." Whether that particular story happened exactly as it's told, and most historians who study this era treat it as a colorful exaggeration rather than a precise record, Archimedes did not need any embellishment to earn his place in this story. His actual work with shapes, with curves, with the careful measuring of things that don't have straight edges, was extraordinary in its own quiet way, and it reached forward across nearly 2,000 years to touch ideas that wouldn't be fully developed until long after his own life had ended. Let me walk you through one of his results slowly, because it's a genuinely beautiful piece of reasoning, and it deserves to be turned over gently rather than rushed past. Picture a sphere, a perfectly round ball, resting inside a cylinder that fits it exactly and snugly, the way a tennis ball might fit inside a can, sized precisely to hold it, touching the sides, touching the top, touching the bottom, with no extra room anywhere. Archimedes worked out that the volume of that sphere is always exactly 2/3 the volume of the cylinder surrounding it. Not roughly 2/3, not close to 2/3, exactly 2/3 every single time, no matter how large or small the sphere happens to be. And the surface area follows this very same clean, exact relationship as well. Archimedes considered this particular discovery so meaningful, so representative of everything his life's work had been about, that he asked for it to be carved onto his own tombstone when he died, a small sphere resting inside a cylinder, a quiet mathematical epitaph. There's a gentle story attached to this too. Long after Archimedes had died, a Roman writer named Cicero was traveling through Sicily, and he went looking for that overgrown, forgotten tombstone, using nothing more than old written descriptions of the carving to guide him. And he found it, tucked away and neglected, simply because he recognized the shape, a sphere resting quietly inside a cylinder, exactly as it had been described. Even the location of a person's grave, it turns out, can be found again through geometry, through the simple, dependable shape of a memory carved in stone. Archimedes also worked out an extremely careful, extremely close approximation for that quiet, constant number we now call pi, the relationship between how far it is around a circle and how far it is across one. And the method he used for this is worth understanding slowly, because it shows something important about how this kind of thinking grows and expands over time. He drew a many-sided shape just inside a circle, with every corner touching the circle from within, and he drew another many-sided shape just outside that same circle, touching it from without. He understood that the true distance around the circle itself had to fall somewhere between the distance around the inner shape and the distance around the outer one, since the circle bulges gently past the inner shape, but stays neatly inside the outer one. Then, patiently, he doubled the number of sides on both shapes, again and again, from 6 sides up to 12, then 24, then 48, and further still, recalculating each time. And as the shapes gained more and more sides, they hugged the circle more and more closely, from both directions at once, squeezing that unknown number into an increasingly narrow, increasingly certain range. Through this slow, careful process, using nothing but patient reasoning about shapes with many sides, Archimedes arrived at a value for pi accurate to about 2 decimal places, more than 2,000 years ago, without any of the instruments or calculating tools we might reach for today. This particular method, of squeezing an unknown curved measurement between 2 known straight-edged ones, and then making those straight-edged approximations tighter and tighter without ever quite touching the curve itself, turned out to be a distant ancestor of an idea that sits at the very foundation of a much later branch of mathematics, one that wouldn't be properly developed until roughly 2,000 years after Archimedes first reasoned his way toward it. Not long after Archimedes, another Greek thinker turned his attention to a different family of curved shapes, the curves you get by slicing through a cone at different angles. Slice straight across, and you get a circle. Tilt the slice slightly, and that circle stretches gently into an oval shape, what we now call an ellipse. Tilt the slice further still until it runs exactly parallel to one side of the cone, and you get an open curve that never closes back on itself. And if you slice through both halves of two cones joined together at their points, you get a pair of curves that mirror each other, opening outward in opposite directions. This thinker worked out the properties of all these curves with extraordinary care, purely as an exercise in curiosity, with no practical use in mind at all, simply because the shapes themselves seemed worth understanding. And here's the part of this story I want you to sit with for a moment, because it's a pattern we'll return to more than once tonight. Nearly 1800 years after these curves were first worked out, purely for their own sake, in a quiet workshop with no telescope in sight, a different mathematician realized that these very same curves describe something real, something enormous, something that had nothing at all to do with cones or slicing angles. He realized that the paths planets trace as they move around the sun are not perfect circles, as people had long assumed, but these same gentle oval curves, worked out centuries earlier by someone who had never once looked up at the night sky with any scientific purpose in mind. An idea explored purely out of curiosity, with no use at all in view, turned out, many lifetimes later, to be exactly the language needed to describe the actual movement of worlds. Let's rest here a moment, and let that pattern settle in gently before we continue. Ideas developed for their own sake, out of nothing more than quiet curiosity about shape and pattern, keep turning out, decades or centuries later, to be precisely the tools needed to describe something real, something physical, something nobody involved in the original thinking could have possibly anticipated. You don't need to remember any particular name attached to this pattern. You only need to notice the shape of it, the way patient, purposeless curiosity keeps quietly paying forward, across centuries, into uses nobody could have predicted at the time. There's one more thread from this era, worth mentioning gently before we move on, because it stayed genuinely unresolved for far longer than almost anything else in this whole long story. Working within their strict tradition of solving every problem using only two simple tools, an unmarked straight edge and a compass, Greek thinkers became fascinated with three particular challenges: constructing a square with exactly the same area as a given circle, constructing a new cube with exactly twice the volume of a given one, and dividing any angle into three perfectly equal parts. Generation after generation of careful minds, spread across many different centuries and many different cultures, attempted these three problems, and generation after generation quietly failed, without ever fully understanding why. It wasn't until many centuries later, using an entirely different kind of mathematical tool than anything available to those original thinkers, that it was finally proven, with complete certainty, that all three of these constructions are genuinely impossible using only those two ancient tools, no matter how patient or clever the person attempting them might be. This isn't a story about human limitation, or about nobody being clever enough yet. It's a hard, permanent fact, built directly into the very structure of what those two simple tools can and cannot ever achieve. And there's something quietly comforting in that, if you let yourself sit with it. Sometimes the answer to a question that has resisted solving for a very long time isn't a clever new solution at all, but a proof that no solution was ever possible in the first place. And even that kind of answer, one that closes a door rather than opening one, still counts as real understanding. It still counts as knowledge gently gained, rather than knowledge withheld. Before we drift further, I want to spend just a little more time with what happened to all of this careful Greek thinking after that classical era itself came quietly to an end. Because the story doesn't simply leap forward untouched into modern times. There's a long, essential, gentle middle chapter here, centered largely in cities across the Islamic world, in places like Baghdad and Cairo and Cordoba and Damascus, during a period sometimes called the Islamic Golden Age. Scholars working in these cities didn't just carefully preserve the Greek geometric knowledge that had come before them, translating it patiently into Arabic at a time when much of it had already been lost or forgotten elsewhere. They also extended it, gently, in genuinely new directions. One especially important figure from this period worked mostly in Cairo, and he made foundational contributions to understanding the geometry of light itself, how it travels in straight lines, how it reflects off curved surfaces, how the human eye forms images at all. His careful method combining patient geometric reasoning with deliberate, controlled experiments to test that reasoning against the real world is considered by many historians to be an early and important ancestor of the modern scientific method itself, appearing centuries before that method is usually described as fully taking shape in Europe. This same tradition also expressed itself in an entirely different, more visual and tactile way, through the elaborate geometric patterns woven into tilework, wooden lattice screens, and carved stone facades across the Islamic world, patterns built from interlocking polygons and stars, repeating with a precision that required a deep, practical understanding of angles and symmetry, understanding that in some cases quietly anticipated mathematical ideas that wouldn't be formally described by anyone else for several more centuries. All of this knowledge, carefully preserved, carefully translated, and genuinely extended across those centuries, eventually made its way into medieval and Renaissance Europe, often passing through centers of translation in Spain and Sicily, where old Arabic mathematical texts were rendered into Latin, quietly reintroducing Europe to Greek geometric knowledge that had largely been lost there, while also carrying forward the real advances that had been made in the meantime. If you're still here with me, let your eyes rest closed now, if they aren't already. There's nothing more you need to catch or hold on to from here. Just let this next part settle over you, the way still water settles into whatever shape happens to hold it, without effort, without resistance. We've walked together now through the rope stretchers along the Nile, through the proof seekers of Greece, through Euclid's quiet architecture of definitions and starting points, through Archimedes with his spheres and his patient circles. And soon, if you drift, none of it will need to be remembered at all. It will simply have been heard, once, in the dark, the way a whole slow river passes by a single quiet stone. Now that we've walked slowly through where all of this came from, the rope stretchers along the Nile, the quiet proof seekers of Greece, the great architecture Euclid built out of a small handful of starting points, let's slow down even further and spend real time with how geometry actually works underneath it all. This is the part of the night where we build up the toolkit itself, gently, piece by piece, with plenty of room to let each idea settle before we move to the next one. There's nothing to hold on to tightly here. Just let each piece arrive, rest a moment, and drift on if it needs to. Everything in geometry begins with just a few basic building blocks, and it's worth moving through them slowly, because every more complicated idea we might touch later tonight is really just these same simple pieces, arranged in different ways. The most basic building block of all is the point, an idealized location in space with no size to it at all. Not small, not tiny. Genuinely no size whatsoever, a pure position and nothing more. It might seem like a strange thing to build an entire field of study around, something with no size at all, but that very abstraction is what gives geometry its quiet precision. Because a point has no size, it has no blur, no uncertainty about where exactly it sits. It simply is, at one exact place, and nowhere else. From a point, we move outward to a line, which you can picture as an endless, perfectly straight path, stretching in both directions forever, made up of infinitely many points, lined up with no gaps between them at all. A line has length, in the sense that it goes on, but no width, no thickness whatsoever. You have never actually seen a true geometric line, and you never will, because any line you could draw, with a pencil, with anything at all, carries some small width of its own. The lines we draw are always stand-ins, gentle approximations, for a perfectly thin, idealized thing that lives only in careful reasoning, never in the physical world around you. If you take just a portion of a line, bounded by two specific points rather than stretching out forever, you get what's called a line segment, probably closer to what you picture when you imagine a straight line drawn on paper, a finite stretch with a clear beginning and a clear end. And when two line segments meet at a shared point, called a vertex, the opening between them, the amount of turning from one segment's direction to the others, is what we call an angle. Angles are measured in units called degrees, and a full circle, as we mentioned earlier tonight, is divided into 360 of them, a quiet inheritance from the ancient Babylonians and their number system built around groups of 60. A right angle, the kind we spent real time with earlier through the Egyptian rope and its neat 3-4-5 triangle, is exactly 90 degrees, a quarter of the way around a full circle. An angle smaller than that is called acute, a word that simply means sharp, because these angles do tend to look narrow and pointed. An angle larger than 90 degrees but smaller than a full 180 is called obtuse, meaning blunt, because these angles open more widely, more gently than a sharp one does. And an angle of exactly 180 degrees isn't really a visible angle at all anymore, just a perfectly straight line, since the two segments point in exactly opposite directions from their shared point. Let's rest with triangles for a while now, a little more deeply than we did earlier, because triangles hold a particularly special place in this whole story, for reasons that go beyond the sturdiness we already talked about. Any triangle at all, no matter how stretched or squashed or tilted it happens to be, has 3 sides and 3 interior angles, and here's a fact worth turning over slowly. Those 3 interior angles, no matter what shape the triangle takes, no matter how long or short its sides are, always add up to exactly 180 degrees, always. A very tall, narrow triangle, a wide, flattened one, a perfectly even triangle where all 3 sides match exactly. It doesn't matter at all. The 3 angles inside will always sum to 180 degrees, every single time, without exception. This fact might feel almost too simple to be worth mentioning, but it's actually a genuinely deep property of flat, even space, the kind of space you're resting in right now. Triangles come in a few different families, worth knowing gently by name, since we may hear these words again before the night is through. An equilateral triangle has all 3 sides equal in length, and as a quiet consequence, all 3 angles equal too, each one exactly 60 degrees. An isosceles triangle has exactly 2 sides equal, with the 2 angles across from those matching sides equal to each other as well. A scalene triangle has all 3 sides different, and correspondingly, all 3 angles different too. And a right triangle, the one we spent so much time with earlier, has 1 interior angle that lands exactly on 90 degrees. Let's move gently now to 4-sided shapes, called quadrilaterals, since this family holds many shapes you already live alongside, without necessarily naming them this way. A square has 4 equal sides and 4 right angles. A rectangle also has 4 right angles, but its sides come in 2 matching pairs, rather than all 4 being identical. Think of a door, or a book resting somewhere nearby, or the shape of the room itself. A parallelogram has 2 pairs of sides that run in the same direction and never meet, no matter how far they're extended, though its angles aren't necessarily square at all, more like a rectangle that's been gently pushed sideways, leaning at a slant. A rhombus has 4 equal sides, like a square, but its corners can lean, giving it more of a diamond-like appearance. And a trapezoid has just 1 pair of sides that run parallel to each other, with the remaining 2 sides angling inward or outward on their own. Beyond 3 and 4 sides, shapes with even more sides fall under the broader word polygon, built from old roots simply meaning many angles. A pentagon has 5 sides, a hexagon has 6, a heptagon 7, an octagon 8, and onward from there. A polygon is called regular when every one of its sides matches in length, and every one of its angles matches too, the way a stop sign is a regular octagon, 8 equal sides, 8 equal angles, holding its shape evenly all the way around. There's a gentle pattern worth noticing here, one that quietly echoes that fact about triangles, always summing to 180 degrees. As a regular polygon gains more and more sides, its corners soften, its angles widen, and the whole shape starts looking less like a polygon at all, and more like a circle, the way a very many-sided shape begins to blur, in the mind's eye, into something smooth and round. This brings us gently to the idea of tessellation, which simply means fitting shapes together to cover a flat surface completely, with no gaps left behind and nothing overlapping. You've likely seen this without naming it, in tiled floors, in brick walls, in the hexagonal cells of a honeycomb. Only a few regular shapes can do this entirely on their own. Equilateral triangles can, because 6 of them fit neatly around a single point. Squares can too, since 4 of their square corners add up perfectly around that same point. And regular hexagons can as well, 3 of them meeting cleanly, which is part of why bees, working purely through instinct and evolution, long ago settled on the hexagon for their honeycomb, the most efficient of these 3 shapes for using the least material while wasting no space at all. A regular pentagon, gently enough, cannot do this on its own, no matter how you try to arrange it. Its angles simply never divide evenly around a point, always leaving a small, awkward gap or a forced overlap behind. There's a related idea worth resting on too, called symmetry, since it quietly threads through nearly every shape we've mentioned tonight. A shape has symmetry when there's some way to move it, by reflecting it as though in a mirror, or by turning it around a central point, so that it lands back exactly where it started, looking completely unchanged. A square carries a great deal of symmetry this way, reflected across several different lines, turned into several different positions, always looking just the same as before. A shape with no symmetry at all, some irregular, lopsided outline, has none of this quiet, self-matching quality. Let's spend real, unhurried time now with area, since this idea sits close to the very beginning of tonight's story. Back with the Egyptian and Babylonian surveyors, measuring flooded fields along a river. Area is simply a measurement of how much flat space a shape covers, how much surface it takes up. Picture a small square, 1 unit long on each side, and the area of any shape is really just asking how many of these small unit squares it would take to cover that shape completely, without any gaps, without any overlap. For a rectangle, this feels almost intuitive once you picture it this way. A rectangle 4 units long and 3 units wide could be covered by 3 rows of 4 small squares each, 12 unit squares in total, which is why a rectangle's area comes simply from multiplying its length by its width. For a triangle, the reasoning takes one more gentle step. Picture any triangle and imagine a second identical copy of it, flipped over and fitted snugly against the first one along one shared side. Together, these 2 triangles form a parallelogram, whose area you already understand, its base multiplied by its height. Since the 2 triangles are equal halves of that same parallelogram, each one holds exactly half that area, which is why a triangle's area comes from taking half of its base, multiplied by its height. For a circle, the reasoning shifts slightly, since a circle has no straight edges to measure along at all. This is exactly where that quiet, constant number called pi returns to the story. The area of a circle comes from pi multiplied by the radius, and then by itself once more. Picture slicing a circle into many thin, narrow wedges, like slicing a whole pizza into a great many slim pieces, and then laying those wedges out, alternating up and down, so they nearly form a rectangle. The more slices you use, the closer that shape comes to a true rectangle, one whose height is the circle's radius and whose width is half the circle's distance around, and multiplying those 2 together brings you gently back to that same familiar formula. Let's lift ourselves, just slightly, out of flat shapes now and into 3 dimensions, into the kind of shape you could actually reach out and hold. A 3-dimensional shape has length, width, and depth all together, and instead of area, we now speak of volume, how much space something actually fills, how much water it could hold, how much material it would take to build. A cube's volume comes from multiplying its side length by itself, and then by itself once more. A rectangular box works the same way, length by width by height. A cylinder, like a can resting somewhere in a kitchen, finds its volume by taking the area of its round base and stacking that upward through its full height. And a sphere, a perfectly round shape, follows a gentle formula worked out long ago through that same elegant sphere and cylinder relationship, connecting this whole quiet toolkit back to where it began. Rest here a while now if you'd like. None of these shapes need to be held onto tightly. They'll keep their same quiet proportions whether you remember them or simply let them drift softly by into sleep. Let's talk now, slowly, about similarity, an idea related to but gently different from that congruence we spent time with earlier. Two shapes are congruent when they are exactly identical, in every possible sense, same size, same angles, same everything. Two shapes are similar when they share exactly the same shape, but not necessarily the same size, the way a small photograph and a larger print of that same photograph are similar to each other. Every angle in one matches the corresponding angle in the other, exactly, and every length in one is simply a scaled version of the matching length in the other, stretched or shrunk by the very same amount throughout the whole shape, evenly, consistently, without any distortion at all. This quiet idea turns out to carry a great deal of power, and it's actually the very thing that let Thales measure that pyramid, using nothing but a shadow, back at the very beginning of tonight's story. His own body and his own shadow formed a small triangle. The pyramid and its shadow formed a much larger one. But because those two triangles were similar, sharing the same shape even though one was so much larger than the other, the ratio between his height and his shadow's length told him, with complete certainty, the ratio between the pyramid's height and its shadow's length too. This same gentle principle, using something small and easily measured, to understand something large and otherwise unreachable, echoes quietly through an enormous amount of practical geometry, in the way a small map represents an enormous landscape, in the way a tiny architectural model represents a building not yet built, in the way a photograph can be made larger or smaller, while every proportion inside it stays exactly, faithfully the same. Let's return now, more slowly this time, to that fifth assumption Euclid built his entire system upon, the one we touched on earlier but didn't fully sit with, because it deserves real attention tonight, and because it leads, eventually, into one of the strangest and most quietly important turns in this whole long story. Euclid's fifth starting point, often called the parallel postulate, is a little more complicated to state than the other four, and it describes, in essence, the conditions under which two lines, if stretched out far enough, will eventually meet. Put a little more simply, though not in Euclid's exact original words, it says this: if you have a straight line and a point somewhere off to the side of it, there is exactly one line passing through that point that runs alongside the original line forever, never touching it, no matter how far both lines are extended in either direction. This might sound almost too obvious to need stating at all. Of course, there's exactly one such line, you might think, picturing a straight line and a point resting just above it. But for well over 2,000 years after Euclid first wrote this down, careful thinkers felt a persistent, quiet discomfort about it, a sense that it was somehow different from the other four starting points, more complicated, less immediately self-evident. Across many centuries, and across many different cultures, mathematicians tried, again and again, to prove that this fifth assumption wasn't really a separate assumption at all, but something that could be derived logically from the first four alone, the way so many of Euclid's other results had been. Every single one of these attempts, across all those centuries, quietly failed. And the manner of that failure turned out to matter far more than success ever could have, though nobody involved could have known that at the time. Rest with that thought for a moment, if you'd like. Sometimes the most important discoveries in any long, patient search aren't the ones that confirm what everyone already believed, but the ones that gently, persistently refuse to confirm it, no matter how many different ways it's approached. For now, though, let's stay a while longer with flat, ordinary space, the kind Euclid was working within, and spend some real time with circles, since we've mentioned them more than once tonight, without quite settling into their inner structure. A circle, at its heart, is simply the set of every point that sits at exactly the same distance from one fixed central point. That central point is called, quite plainly, the center, and the constant distance out to any point on the circle's edge is called the radius. If you draw a straight line all the way through the center, touching the circle on both sides, that full line is called the diameter, and it's always exactly twice the length of the radius, since it's really just two radius lengths. placed end to end, stretching from one edge of the circle, through its very middle, out to the opposite edge. The full distance around a circle, if you traced your finger all the way along its curved edge and back to where you began, is called the circumference. And this is where that quiet, constant number called pi makes its most fundamental appearance in this whole story. The circumference of any circle at all, no matter how small or how vast, is always exactly pi multiplied by the diameter. This ratio, circumference divided by diameter, never changes. It stays exactly the same for every circle that has ever existed or will ever exist. From a circle small enough to trace around a single grain of sand, to one large enough to trace around an entire galaxy. Pi isn't a number anyone decided upon, the way the Babylonians settled on groups of 60, or the way we settled on 360 degrees for a circle. Pi is simply there, quietly built into the very structure of flat space itself, waiting patiently to be found rather than invented. There's one more gentle circle fact worth resting with tonight, because it connects directly back to Thales, the very first person we spent time with earlier, who tried to move geometry from simple trick toward proven certainty. Picture a circle, and picture a diameter drawn straight across it, from one edge, through the very center, to the opposite edge. Now choose any third point at all, anywhere along the remaining curve of that circle, and draw two lines connecting that point back to each end of the diameter. What you'll find, every single time, without exception, is that the angle formed at that third point is always exactly a right angle, always precisely 90 degrees. It doesn't matter whether that third point sits close to one end of the diameter or the other, near the top of the circle or tucked closer to the bottom. The angle simply refuses to be anything other than 90 degrees, held firmly in place by the quiet structure of the circle itself. This gentle result is sometimes called Thales's theorem, and there's something lovely in it. A simple circle, one of the plainest shapes there is, holding a perfectly rigid, perfectly dependable rule inside it, waiting patiently for anyone unhurried enough to notice. A closely related idea involves what are called tangent lines, lines that touch a circle at exactly one single point, without ever crossing into its interior. It turns out that wherever a tangent line touches a circle, it always meets the circle's radius, drawn out to that exact point of contact, at a perfect right angle, every single time, for every circle and every tangent line that could ever possibly be drawn. This quiet fact is at work anytime something moves along a circular path and then releases into a straight line, the way a stone flies outward once it's let go from the end of a swung string. The straight path that stone takes, once released, will always continue exactly along the direction of that tangent line, perpendicular to the radius, at that precise instant, a small, hidden piece of circle geometry gently governing something as ordinary as a stone leaving a spinning hand. Let's slow down here and let all of this settle, the way sediment settles quietly to the bottom of still water. A point, with no size at all, a line, stretching endlessly in both directions, an angle, the small opening where two lines meet, a triangle, holding its three angles together at exactly 180 degrees, no matter how it's stretched or leaned. A circle, holding pi quietly within its curve, holding a perfect right angle within its diameter, wherever a third point happens to land along its edge. These simple pieces, resting quietly beside each other, are really the entire foundation beneath everything more complicated we might touch later, if you're still listening, or beneath everything you'll simply drift past, if your eyes have already closed. There's a kind of stillness in geometry that's worth noticing now, something separate from the history, separate from the names and dates and centuries we've walked through tonight. It's the stillness of something that simply is, and always was, waiting quietly to be described. The 3-4-5 triangle worked for Egyptian surveyors along a flooding river, long before anyone understood why it worked. The right angle hiding inside every circle's diameter was there for Thales to notice, patiently, the way it's still there now, in every circle drawn or imagined anywhere. Pi sat quietly inside the relationship between a circle's edge and its width, long before Archimedes patiently squeezed it between many-sided shapes to narrow down its value. None of these truths were created by the people who found them. They were simply resting there, in the structure of space itself, the same structure holding up the room around you right now, the same structure holding the shape of your own body against the mattress beneath you. You don't need to hold on to any particular piece of this. Not the names, not the exact wording, not even the shapes themselves, if your mind has already begun to loosen its grip on all of it. What matters, if anything does right now, is only the quiet feeling underneath it all, that the space around you, the space holding you, has always followed a small handful of patient, dependable rules, whether or not anyone was awake to notice them. A triangle's angles will always meet at 180 degrees. A circle's curve will always hold that same quiet number, pi, inside its relationship between edge and width. A tangent line will always meet its radius at a perfect right angle, wherever it happens to touch. These things were true long before tonight, and they'll stay true long after you've drifted off, long after this recording has ended, long after the room around you has gone fully silent. Let yourself rest here a while. There's nothing more to reach for in this part of the story. Just the quiet, dependable shapes, holding their places, the way they always have, the way they always will, whether you're awake to notice them or not. Let's move now, gently, into a new chapter of this story, because after Euclid, and after Archimedes with his spheres and his patient circles, geometry did not stay frozen in its original Greek form. It kept extending outward, quietly, into territories that would have startled even the careful minds who came before. Territories that eventually reached forward, centuries later, into the room where you're resting right now. The first major extension came from a source you might not expect at all, algebra, and it arrived through the work of a French thinker named René Descartes, working in the early 1600s, nearly 2,000 years after Euclid had first laid down his careful starting points. Descartes had a realization that sounds almost simple once it's explained, though it quietly changed the whole character of geometry going forward. He proposed that you could describe the exact location of any point on a flat surface using just two numbers, one telling you how far to move sideways from a fixed starting point, and one telling you how far to move up or down. This might feel familiar to you, in some distant, half-remembered way, because it's essentially the coordinate grid many of us met once in a classroom, now carrying his name, Cartesian coordinates, quietly honoring the man who first proposed it. What Descartes understood was that once every point can be described with numbers this way, entire shapes can be described with equations instead of drawings. A circle, that same gentle shape we spent time with earlier tonight, that quiet ring of points all sitting at exactly the same distance from a center, can be written as a single equation connecting those two numbers. A straight line can be written even more simply. And once shapes become equations rather than physical drawings, you can use the tools of algebra, methods for solving, methods for finding where two paths cross, to answer geometric questions without ever touching a straight edge or a compass at all. This blending of algebra and geometry came to be called coordinate geometry, and it represented something genuinely new, a way of holding shape not through construction, the way Euclid always had, but through pure number and symbol. This shift turned out to carry real weight, because it meant that problems which had resisted straight edge and compass for 2,000 years suddenly opened up through algebra instead. It also allowed for curves far more intricate than anything the Greeks had ever systematically studied, curves defined by equations more complicated than the gentle ones needed for circles or the conic sections we touched on earlier. And it set the stage, only a few decades later, for an entirely new field called calculus, developed independently by Isaac Newton and Gottfried Leibniz in the latter half of that same century, a set of tools for understanding how things change, moment by moment, point by point, along a curve. Closely related to this, growing up alongside it though with roots reaching back much further, into Old Greek and Indian and Islamic mathematics, is a field called trigonometry, focused specifically on the relationship between a triangle's angles and the lengths of its sides, particularly for right triangles. The word itself simply means triangle measurement. Trigonometry gives us a small set of steady ratios, ones that describe, with complete consistency, how a right triangle's angles relate to the proportions of its sides, no matter how large or small that triangle happens to be, so long as the angles themselves stay the same, an idea that echoes gently back to that notion of similarity we spent time with a little earlier tonight. These ratios turned out to reach far beyond triangles themselves, because any point moving steadily around a circle traces a path that can be described using these same relationships. Trigonometry quietly became the language for describing anything that oscillates, anything that repeats in a wave-like rhythm, sound moving through air, light traveling as a wave, the gentle back-and-forth vibration of a plucked string. An ancient Greek astronomer named Hipparchus, working around 150 years before the start of our Common Era, is often credited with building some of the earliest trigonometric tables, meant to help predict where stars and planets would appear in the sky. Indian mathematicians working a few centuries later, and Islamic scholars after them, refined and extended these methods considerably, carrying this knowledge forward, patiently, generation after generation, until it eventually settled into medieval and Renaissance Europe. Now let's return, gently, to that thread we set down earlier, and let rest for a while. Euclid's fifth starting assumption, the one about parallel lines that quietly troubled careful thinkers for well over 2,000 years. In the early 1800s, working somewhat apart from one another, a Hungarian mathematician, a Russian mathematician, and a German mathematician who was already considered one of the finest minds of his century, each arrived at a similar and rather startling thought. Instead of continuing that 2,000-year effort to prove Euclid's fifth assumption had to be true, what would happen if someone simply assumed it wasn't, and then followed that assumption wherever it led, however strange the path became? This might sound like it should lead somewhere broken, somewhere filled with contradiction. And for a long time, that's exactly what everyone quietly expected, that denying something so apparently obvious would eventually collapse into nonsense, proving, in a roundabout way, that the original assumption had been necessary all along. But that isn't what happened. Instead, these three thinkers found that you could build an entirely consistent, entirely coherent alternative geometry, one where, through a single point beside a line, there might be many different lines running parallel to it, rather than just one, or, in another version entirely, none at all, every pair of lines destined to cross no matter how carefully they're drawn. To feel how this is even possible, it helps to picture curved surfaces rather than flat ones, because that's really what's happening underneath all of this. Picture the surface of a saddle, the kind resting on a horse's back, curving gently upward on two sides and downward on the other two. On a surface shaped this way, lines that would stay perfectly parallel on a flat table begin, instead, to drift apart from each other the further they travel. And you can draw more than one line through a single point that never touches a given line at all, each one still following the shortest possible path between its own two ends, which is really all a straight line ever means, once you're standing on a surface that curves. Now picture the opposite kind of curve, the surface of a sphere, the way the Earth itself curves gently beneath you right now. On a sphere, there's no such thing as truly parallel lines at all. Every great circle, meaning a circle that wraps all the way around and cuts the sphere exactly in half, the way the equator does, or the way any line of longitude does, running from pole to pole, will eventually cross any other great circle, no matter how carefully you draw them. Picture two lines of longitude, running side by side near the equator, seeming for a moment as though they'll never meet. But follow them northward, patiently, and they draw closer and closer until they meet exactly at the pole. What looked parallel at one point along their length was quietly converging the entire time. And here's something else that gently shifts on a sphere, something that reaches back to that fact about triangles we spent real time with earlier, that their three angles always add to exactly 180 degrees. On a curved surface, that quiet rule softens. Picture a triangle that begins at the very top of a sphere, travels straight down to its middle, turns a perfect corner, travels a quarter of the way around, turns another perfect corner, and travels straight back up to where it began. That triangle's three angles add up to more than 180 degrees, because the surface itself is curved, and the rules that felt so completely universal earlier tonight turn out to belong specifically to flat space, not to every possible space. This whole family of alternative geometries came to be called non-Euclidean geometry, and for a long while after those three thinkers first developed it, it remained a quiet, elegant curiosity within mathematics, an interesting demonstration that alternatives to Euclid's system were logically possible, without any obvious connection to the physical world people actually moved through. That changed, gently but completely, in the early 20th century, when Albert Einstein published his theory of general relativity and revealed that the actual geometry of the universe we live inside is not flat in the way Euclid imagined, but curved, in exactly this non-Euclidean way, bending around anything with enough mass, a star, a planet, the very earth beneath you now. What we experience as gravity, in this understanding, is simply an object following the straightest possible path through space, that is, itself, quietly curved. There's something worth resting with here, something that connects the whole shape of tonight's story together. A purely abstract exploration, born from mathematicians' patient, 2,000-year discomfort with a single sentence buried inside an old Greek text, developed with no practical purpose in mind whatsoever, turned out, a century later, to be exactly the language needed to describe how gravity actually behaves in the real universe. Nobody working on this in the early 1800s was thinking about gravity at all. They were simply following a quiet question about parallel lines wherever it happened to lead, purely out of curiosity, and that quiet following turned out, generations later, to answer one of the deepest questions about the physical world. Let's rest here a while longer, and let this particular thread settle fully before we move any further. A saddle curving gently in two directions at once, a sphere curving evenly all the way around, lines that spread apart on one surface, lines that quietly converge on the other, a triangle's angles, holding steady at 180 degrees on a flat table, softening into something different once that table curves. And underneath all of it, the same quiet space that holds the room around you right now, curving, ever so slightly, around everything with enough weight to bend it, around the earth itself, around you, resting there, held gently in place by a curve too vast and too gentle to ever really feel. You don't need to hold on to the names or the exact shape of a saddle or the precise reasoning behind any of it. What matters, if anything does right now, is only the soft, settled feeling underneath this whole idea, that even the space around you, the space you're lying inside at this very moment, has a shape of its own, quiet and curved and patient, whether or not anyone is awake to notice it. Let that thought rest beside you now, the way a held breath finally lets go, the way a curve settles gently back toward stillness. Let's talk now about a few more branches of this long, patient story, moving a little more slowly through each, letting them settle one at a time, the way footsteps settle into sand. There's a field called topology, and it's a strange, soft kind of geometry, very different in spirit from the precise, rigid shapes we spent time with earlier tonight. Topology studies the properties of a shape that stay exactly the same, even when that shape is stretched, or twisted, or gently bent, so long as it's never torn, never cut, never glued to itself in some entirely new way. In this quiet field, a coffee mug and a donut are considered, in a real mathematical sense, the very same shape, because you could reshape one into the other through slow, continuous stretching, without ever once cutting or tearing anything, since both shapes share exactly one hole passing through them, a mug's handle, a donut's soft center. Topology doesn't care about length or angle or any of the careful measurements Euclid spent so much time with. It cares only about that hole, about how many of them a shape holds, about whatever quiet property survives no matter how much the shape is pulled or pressed or reshaped. There's something soothing in that idea, if you let it settle for a moment. A shape doesn't need to stay the same size, or the same outline, to still be, underneath it all, essentially itself. Whatever holds steady through change, that's what topology is quietly paying attention to. Before we drift toward fractals, there's one more branch worth resting with, because it didn't come from mathematicians at all, at least not at first. It came from painters. During the early Italian Renaissance, in Florence, an architect named Filippo Brunelleschi built a quiet, careful demonstration. He painted a scene of a building in his city, and using a small mirror and a narrow peephole, he showed people that his flat, painted image, when viewed just the right way, created a startlingly convincing sense of real depth and real distance, as though you could step directly into the painting itself. Brunelleschi had worked out, through careful geometric reasoning, exactly how parallel lines, receding into the distance, the way the edges of a tiled floor stretch away from someone standing at one end of a room, needed to be drawn so they converge toward a single point on the horizon, a point we now call a vanishing point, in order to fool the eye into perceiving depth on a surface that is, in truth, entirely flat. This idea was written down a little more formally not long after by another Florentine thinker named Leon Battista Alberti, laying out precise geometric rules for what came to be called linear perspective. And this technique, born quietly out of painting, out of nothing more than an artist's careful attention to how the eye actually perceives space, eventually grew into a full branch of mathematics, called projective geometry, studying exactly this kind of transformation, what happens to a shape's relationships when it's projected from one surface onto another, the way light from a real three-dimensional room falls onto the flat surface of a canvas, or, in a much more modern echo of the same idea, the way light from the world around you falls onto the flat sensor inside a camera, or onto the curved surface at the very back of your own eye, right now, even in the dark, even with your eyes closed. There's something gentle in this thought, too. Long before anyone had formal mathematics for it, a painter simply noticed how light behaves, how distance quietly bends what we see, and turned that noticing into something precise enough to eventually become its own field of study. Sometimes understanding begins not with an equation at all, but with someone simply paying close, patient attention. Let's move now towards something a little more recent, something called fractal geometry, largely connected to the work of a mathematician named Benoit Mandelbrot, working in the second half of the last century. Fractal geometry studies shapes that hold a quiet property called self-similarity, meaning the shape looks like itself at every scale you examine it, so that if you zoom in, closer and closer, you keep finding smaller versions of that very same pattern, repeating, gently, again and again, without ever quite stopping. Mandelbrot came to this quietly, through a deceptively simple question: how long is the coastline of Britain? It sounds like it should have an easy answer, doesn't it? But he realized that the answer depends entirely on how closely you choose to measure it. Measure with a large ruler, taking big, sweeping steps along the coast, and you get one length. Measure with a much smaller ruler, one that follows every small inlet, every jagged little rock formation, the larger ruler skipped right over, and you get a longer measurement. And this keeps happening. The coastline keeps growing longer and longer, the more finely you measure it, without ever quite settling on one single final number, because real coastlines hold this same rough, repeating, self-similar quality at nearly every scale, from the shape of an entire bay down to the shape of one single stone resting along the shore. There's a soft kind of wonder in that, if you let yourself rest with it. A coastline doesn't have one true length at all. It simply has as much detail as you're willing to notice, unfolding further and further the closer you choose to look, the way a single held breath can hold more stillness inside it than you first expected, if you simply stay with it a little longer. Let's bring all of this back now, gently, out of history, out of abstraction, and into the quiet room around you, because everything we've walked through tonight isn't locked away in some old book, some distant lecture hall. It's resting quietly, all around you, right now, in this exact moment. Think of the device that may have played this recording for you, resting somewhere nearby. Its screen, if you looked at it earlier, is built from a soft grid of tiny points, each one holding its own precise location, an echo of that very same coordinate system Descartes first imagined 400 years ago, now guiding, quietly, which of a screen's countless tiny lights should glow, and in which color, at every passing moment. Think of the walls around you, meeting the ceiling at something close to a right angle. That corner is a distant descendant of the Egyptian rope stretchers we spent time with at the very beginning of tonight, the same 3-4-5 triangle, still quietly at work today, though now through laser levels rather than knotted rope, still resting on that very same ancient principle. Think of your own body, resting there in the dark. The gentle spiral coiled inside nearly every cell of you follows its own steady geometric structure, a spiral that stays remarkably consistent, generation after generation, quietly carrying forward everything that makes you who you are. Your bones themselves lean on geometric efficiency too, hollow, cylindrical shapes in your arms and legs, holding real strength while carrying far less weight than a solid shape would require. The same quiet principle engineers still reach for when designing something light enough to lift, yet strong enough to hold. If you happen to be somewhere you could see the night sky, though of course, right now, your eyes are closed, and you're only seeing it in memory, know that the planets tracing their slow paths above you are following curves a mathematician in Alexandria once worked out purely for the pleasure of it, nearly 2,000 years before anyone realized those same curves described the actual motion of worlds. And even the quiet sound in the room around you, if there's a fan running somewhere, or the soft hush of distant traffic, moves through the air in a wave, describable through the very same gentle ratios that trigonometry first developed to describe triangles, not sound at all, and yet here it is, still quietly at work, carrying that sound toward you, wave after wave, all the way to where you're resting now. Think, too, of the honeycomb, hexagonal cells fitted together with no wasted space between them, a shape bees settled into through nothing more than patient evolution, long before anyone proved, formally, that it was the most efficient shape for the task. Nature, it turns out, tends to find its own quiet, efficient solutions long before human reasoning ever catches up to explain why they work so well. And think of the domes resting atop old buildings in cities you may have visited or only imagined, distributing their weight evenly across a curved surface in a way flat roofs simply cannot manage. And the long, gentle curve of a suspension bridge's cables, following almost exactly the same kind of curve Apollonius once studied, purely out of curiosity, centuries and centuries before anyone needed it for a bridge at all. Even the soft folding of a cardboard box, flattened for storage and then gently popped back into its full shape, leans on principles connected to this same quiet field, principles that also help satellites fold their solar panels down small enough for launch, only to unfold again, slowly, once they've reached the stillness of space. Rest here a while now, and let all of this settle, the way sediment finally, fully settles at the bottom of still water. None of it needs to be remembered. None of it needs to be held onto with any effort at all. The geometry was here before tonight, quietly shaping the room around you, the walls, the corners, the curve of the bed beneath your body, and it will still be here tomorrow, whether or not you carry a single word of it forward with you into the morning. Let your breathing slow, if it hasn't already. Let your thoughts loosen their grip, the way a hand slowly opens once it's finally allowed to rest. There is nothing left to understand right now, nothing left to hold, only the quiet shapes around you, patient and unchanging, the same shapes that have always been here, waiting, the way they always will. Let's rest here a while longer, and let a few more quiet corners of this world settle into place, gently, one at a time. Think of salt resting on a plate, or any crystal at all, snowflakes, quartz, small clear stones tucked away in a drawer somewhere. Every crystal grows according to a strict, repeating symmetry, atoms arranging themselves into the very same small handful of patterns, over and over, whether that crystal is forming deep underground, in a careful laboratory, or quietly falling through a cold winter sky, outside a window somewhere tonight. Mathematicians once proved that there are exactly 17 distinct ways to cover a flat surface with a repeating symmetric pattern, no more, no fewer, a complete, closed little catalog, not unlike that earlier proof that only 5 regular solids can ever exist. An artist named Escher, working through much of the last century, became quietly fascinated with these same 17 patterns after visiting an old palace in Spain and studying its tilework closely, and he spent years drawing careful, interlocking birds and fish and lizards, without fully realizing, at first, that he was walking the very same patterns mathematicians had only just finished classifying, from the opposite direction entirely. And even that stranger, curved geometry we touched on earlier tonight, the kind where triangles hold less than their usual amount, and parallel lines drift gently apart rather than staying evenly spaced, turns out to have a real, tangible presence in ordinary life. In the ruffled edges of certain leafy vegetables, in coral, growing slowly along a reef, in the delicate frills of a small sea creature. These living shapes grow this way simply because their cells behave this way, and in recent years, someone found she could recreate this same soft curved surface using nothing more than yarn and a crochet hook, adding stitches steadily as she worked outward, until an idea once considered purely abstract sat gently in the palm of her hand, soft, ruffled, and completely real. There's a quieter pattern, too, worth resting with for just a moment, one that shows up in the markings on a giraffe's coat, in the way dried mud cracks apart along a riverbed, in the small, uneven cells of a dragonfly's wing. It forms whenever a surface divides itself based on closeness to a scattered handful of points, each region simply claiming whatever space sits nearer to it than to any other point nearby. Nature seems to reach for this pattern again and again, without any planning at all. The same quiet solution appearing in skin, in roots pushing through soil, in almost anything that needs to divide space fairly among many small centers. And there's one more place worth mentioning gently, tucked inside a hospital, inside the quiet machines that can see inside the human body without ever needing to open it. A scan like this works by passing many thin beams through the body from many different angles, and then patiently reconstructing all of those angled readings into one coherent picture, layer by layer. The mathematics behind this was worked out decades before any such machine existed to use it, another quiet example of an idea, developed simply for its own sake, waiting patiently until the world finally needed it. Let's slow down now and spend a little time with the parts of this story that remain unfinished. The corners mathematicians still gently argue over, even now, even after all these thousands of years of careful thought. This isn't meant to unsettle you at all. It's really more of a soft, quiet wonder, a reminder that even something as old and as carefully studied as geometry still holds a little genuine mystery inside it. There's a question, simple enough to state, about the most efficient way to stack identical spheres together, the way you might stack oranges in a crate, so they take up the least possible wasted space between them. Grocers have stacked fruit this way for centuries, following instinct alone, arranging them into a familiar pyramid shape. An astronomer once proposed, centuries ago, that this common stacking arrangement really was the most efficient one possible. It seems almost obviously true if you've ever stacked oranges yourself. And yet, proving it with the kind of complete certainty this story has been built on all night took nearly 400 years, arriving only through the patient help of a great many careful computer calculations, checked and rechecked for over a decade before anyone felt confident enough to call it settled. There are other, closely related questions about stacking shapes efficiently that remain entirely open even now, questions nobody has yet answered with full certainty, resting quietly at the edge of what's currently known. There's a similar softness around certain fractal shapes too, the kind we touched on a little earlier tonight. One of the most famous of these, generated through a surprisingly simple, repeating process, holds an endless, never quite repeating complexity along its edge, new swirling patterns, and small copies of itself nested inside itself, no matter how closely you look. Some very simple-sounding questions about the exact structure of that edge remain unanswered. Quiet threads mathematicians are still gently pulling on today. There's a deeper, softer question resting underneath all of this too, one that doesn't really have a clean answer at all. When we speak of a perfect circle or a perfect triangle, the kind with no real width or thickness, existing only in careful thought, what exactly are we speaking of? Do these perfect shapes exist somewhere on their own, waiting quietly to be noticed, the way an old philosopher once believed? Or are they simply useful ideas, gently built by human minds to help make sense of the physical world, with no existence at all outside of that thinking? This question, whether these shapes are found or simply made, has never been fully settled, and serious thinkers still land in very different places on it, even today. There's the quiet question of dimension too, something we've mostly left alone tonight, resting comfortably with flat shapes and ordinary solids, the kind you could reach out and hold. But mathematicians work, quite seriously, with spaces of 4 dimensions, 5, any number at all, far beyond anything a person could ever picture directly. This isn't fiction, it's a real, well-established field, with real applications in physics, where some theories describing the deepest structure of the universe quietly require more than the 3 dimensions we move through each day, dimensions theorized to be curled so small, so tightly, that we have no way of noticing them at all in ordinary life. Whether these hidden dimensions are truly out there, or simply a useful way of making certain equations behave, is a question still resting, unresolved, at the edge of what physics currently understands. Before we let this particular thread go, there's one question worth mentioning that no longer needs to rest on this quiet list, even though it did for nearly 100 years, because the story of how it was finally answered is a gentle one, worth hearing before we drift onward. Picture a shape with no holes anywhere inside it, where every loop of string wrapped around any part of it could always be pulled tight into a single point, without ever snagging on some hidden handle. A French mathematician once asked whether any 3-dimensional shape with this quiet property had to be, underneath it all, essentially the same as a simple sphere. This question sat unanswered for very nearly a century, resisting the careful efforts of many of the most capable minds of that era. Eventually, an organization offered a considerable reward for a correct, fully verified answer, and a Russian mathematician, working mostly alone, quietly posted a solution online rather than through any of the usual formal channels, building on decades of earlier work, but finishing what nobody else had quite managed. It took the wider mathematical community several more years of careful, patient checking before everyone agreed the solution held. And then something gentle and unusual happened. That mathematician was offered both the prize money and one of the field's highest honors, and he quietly declined both, feeling that the attention missed the entire point of the work itself, before slowly stepping back from public life altogether. There's something fitting in that, somehow. A century-old question about pulling a loop tight into a single point, finally answered by someone who then, in his own quiet way, pulled back from everything the answer might have brought him. And finally, let's rest once more with the largest question of the night, the one about the actual physical shape of the universe itself. Scientists who study the universe as a whole still don't know, with complete certainty, whether it is flat, the way ordinary geometry describes, where parallel lines never meet and triangles hold exactly 180 degrees, or whether it curves gently back on itself somewhere, far beyond what anyone has yet been able to measure. The most careful observations available, drawn from the oldest light in the entire universe, suggest it sits very close to flat indeed, remarkably close, though not so precisely measured that a very gentle curve, in either direction, can be entirely ruled out. A question this large, the true shape of everything that exists, remains, even now, gently unresolved. There's a certain kind of comfort tucked inside all of this uncertainty, if you let yourself rest with it for a moment. Geometry began, all those thousands of years ago, with people solving very small, very grounded problems, remeasuring a flooded field, laying one careful stone beside another, and it has grown, slowly, across all that time, into something that now quietly touches the shape of everything that exists, questions that remain honestly, gently open. That isn't a flaw in the story at all. That's simply what a living field of understanding looks like, still reaching, even after 4,000 years, towards something it hasn't fully held yet. By now, you may have drifted in and out more than once. That's exactly as it should be. There's nothing to catch up on, nothing you've missed that matters. Everything has been settling quietly in the background this whole time, whether you were following closely or already halfway towards sleep, the way a room slowly warms even when nobody is watching the thermostat. Just keep resting now. There's nothing left that needs your attention at all. If you were to hold all of tonight in a single image, here is what it might look like. Picture a single point of light, resting alone, with nothing around it at all. No size, no direction, nothing but pure, quiet location. That's where geometry begins, the simplest idea there could ever be. Now let that point stretch softly outward in one direction, becoming a line, and let a second line cross it, forming a small angle where they meet. Let three such lines close gently together into a triangle, the most steady shape there is, the same shape that held up temple corners in ancient Egypt, and still, in its own quiet way, holds up the room around you tonight. Let that triangle's own hidden law, the relationship between its sides that Pythagoras and his followers once proved, ripple softly outward through everything else, through circles, through spheres, through the slow curved paths of planets, through satellites quietly helping some device know exactly where it rests on the surface of the world. Now let that flat world curve gently into something new, a saddle, a sphere, the actual fabric of space and time itself, bending softly around every star and every planet in the universe, including the very one you're resting on right now. Let the straight edge and compass of the old Greek thinkers give way, slowly, to Descartes' quiet numbers and coordinates, and let those numbers give way, centuries later, to the countless small triangles that make up every curved shape you've ever seen, glowing softly on a screen. Let one stubborn question about parallel lines, turned over patiently for 2,000 years by people who never once doubted an answer would eventually come, quietly become the very language Einstein needed to describe gravity itself. Let a Greek thinker's quiet curiosity about slicing cones become, 18 centuries later, the exact shape of a planet's path around its sun. Let a Hungarian, a Russian, and a German each open a door nobody else had thought to open, and find, resting calmly on the other side, not confusion at all, but an entirely new, entirely consistent universe of shape. This is what geometry actually is, once you've heard the whole of it, slowly, the way we have tonight. It was never a fixed set of rules, handed down once and never questioned again. It's something more like a quiet inheritance, passed gently from Egyptian rope stretchers to Babylonian scribes, to Greek philosophers, to Islamic scholars, to Renaissance painters, to careful 19th century mathematicians who dared to wonder whether a 2,000-year-old assumption might not be as necessary as everyone had believed. Each generation received what came before, found the small cracks resting quietly inside it, the places where the old rules didn't quite explain everything, and pushed, gently, just a little further into what lay beyond. And it never once stopped being useful, even at its strangest, even at its most abstract, because the shape of a cone, sliced at just the right angle, turned out to be the shape of a planet's whole year, and the shape of curved, unfamiliar space turned out to be the true shape of gravity, and the same flat triangles once used to gently approximate a circle in ancient Syracuse are the very same flat triangles quietly approximating curved surfaces inside every screen you'll ever rest your eyes on again. Geometry, in the end, is simply the quiet study of how things fit together in space, how far apart they rest from one another, what angles they form, what paths they trace as they move. And you are, always, resting somewhere inside it, a shape settled onto a curved surface, orbiting a star along a path a curious Greek thinker could have described, long before anyone knew what it meant. Held gently in place by a curve in space-time that Einstein finally understood, made of countless small cells whose quiet structure follows patterns bees found through nothing more than patient evolution, long before anyone proved those patterns were the most efficient shapes of all. You were never separate from any of this. You've simply been resting inside it, quietly, the whole time, the same way you're resting inside it right now, in this room, on this night. There's nothing left to explain now, only to notice, softly, if you'd like to. Feel the shape of whatever is beneath you, holding your weight in the particular curve it has settled into around your body. Feel the corners of the room around you, wherever they happen to be, meeting at those same quiet right angles the Egyptians once found using nothing more than a length of knotted rope, thousands of years before either of us existed. Somewhere above the ceiling, above the roof, satellites are still tracing their slow, patient paths, the very same curves a mathematician once worked out on paper in Alexandria, for no real reason at all, except that he found them beautiful. Those same curves would later help someone prove how worlds move. And now, tonight, this very moment, they're quietly helping some small device somewhere know exactly where it rests on the surface of a planet that is, itself, only another gentle curve, drifting through a curved space Einstein finally came to understand, inside a universe that may, in its largest and most distant shape, still be something no one has fully measured. You don't have to hold on to any of that. You were never required to. The three sides of a triangle will keep their same quiet, locked relationship together, whether you remember the reasoning behind it or not. The bees will keep building their soft hexagons. The planets will keep tracing their slow, patient ellipses. The light in this room, if there's any light at all, will keep bending exactly the way it always has, whether you're awake to notice it or already resting somewhere past thought. All of it keeps working, quietly, patiently, without ever needing your attention. So let your attention go now, gently, the way a coastline slowly blurs into softer and softer detail the less closely you look at it. The way a circle seems to emerge, softly, from a many-sided shape, once it holds enough sides that its corners simply disappear. You don't need any more edges tonight. You don't need any more angles at all. Just the soft, rounded absence of them, the shape sleep tends to take, once nothing is measuring it anymore. Rest now. Let your breathing settle into whatever rhythm feels most natural, slow and unhurried, the way a tide settles once the wind has gone still. There's nothing left tonight that asks anything of you. Every idea we walk through together, the rope stretched taut across a flooded field, a triangle's three sides locked into their quiet, permanent relationship, a circle's soft curve holding pi inside it, a saddle-shaped surface bending space in ways Euclid himself could never have imagined. All of it will still be exactly where we left it, waiting patiently, whether you carry a single piece of it into tomorrow or none at all. You began tonight as a shape resting on a curved surface, held gently by an invisible pull toward the center of a planet you cannot see, and you remain that shape now, a little heavier perhaps, a little softer, the edges of your thinking slowly rounding off the way a many-sided figure rounds itself into something close to a circle. There is nothing left to solve. There is nothing left to prove. The theorems will hold their shape without you standing watch over them. The pyramids will keep their ancient angles. The planets will keep their old and patient orbits. And you, resting here, are simply allowed to let go of all of it now, the way a hand finally opens once it no longer needs to hold anything at all. If your mind still holds a stray thought or two, a half-remembered fact about a rope or a triangle or a curve too vast to ever fully picture, let it drift, the way a small cloud drifts without needing anywhere in particular to go. There's no order left to follow tonight, no sequence of ideas waiting to be checked off one after another. Just this quiet unwinding, this slow softening, this settling of a shape into whatever rest looks like for you tonight. The room around you will keep its geometry long after your thoughts have gone quiet. The corners will stay exactly where they are. The gentle curve of wherever you're resting will keep holding you, the same patient way it has been holding you this entire time. And somewhere far above, whether you can see it or not, the sky continues to hold its own slow curved motion, indifferent to whether you're awake to notice, content simply to keep turning, the way it always has, the way it always will. There's a kind of quiet comfort in that, if you let yourself feel it. You don't have to hold the universe together. You don't have to remember its shape, or its history, or the names of the people who spent their whole lives trying to understand it a little better than the generation before them. You only have to rest, here, now, inside a geometry that has always been steady enough to hold you without asking anything back. So let this be where we leave things tonight. No more history, no more proofs, no more curves to trace or angles to measure, just the soft, dim shape of this room, holding its quiet right angles in the dark. Just the gentle curve beneath you, cradling your weight the way it has been all along. Just your own breathing, slower now, softer now, tracing its own small, private rhythm, needing nothing more from this night than to keep going, gently, until it finally, quietly lets go. Rest now. The shapes will keep their places. The night will hold its geometry without you, for as long as you need it to. There's a stillness that settles in, somewhere around this point in the night, and if you're still here with me, even faintly, even at the very edge of sleep, this last part doesn't ask anything more of you than what you've already been giving all along. Just your breath. Just the slow, steady weight of your body against whatever is holding you up right now. Think back, gently, to where we began tonight, that image of you as a shape, resting on a curved surface, held down by something you can't see or feel directly. Only trust is there, working quietly beneath everything else. That was true then, and it's still true now, this many hours or minutes or half-remembered thoughts later. Nothing about that has changed. The curve of the earth is still curving, the room is still holding its corners. Your body is still finding its own particular shape against the mattress, settling a little more with every breath you let go of. We walked a long way together tonight, all the way from a flooded river in ancient Egypt to the edges of the visible universe. And if any of that stayed with you, wonderful. And if none of it did, that's more than fine too. That was never really the point. The point, if there was one, was simply to give your mind something slow and steady to walk alongside, the way a quiet companion might walk beside you on a long evening path, not needing to talk the whole time, just needing to be there. Let's return, softly, to the simplest image from earlier, because simple images are often the ones that carry us the furthest into rest. A single point of light, no size, no direction, just a location, resting quietly in the dark, the way you are resting now. From that point, a line stretched outward, and from that line, a triangle formed, 3 sides locking into a shape so steady that it has held up temples and towers and the very roof over your head for thousands of years without ever once needing to be reinforced or reconsidered. That kind of steadiness is rare in this world, and it's worth resting inside of for a moment. Some things really do hold their shape, no matter how much time passes, no matter how much the world around them changes, and from that triangle, everything else in tonight's story quietly unfolded. Circles, holding pi gently inside their curves. Spheres, holding 2/3 of a cylinder's volume inside their rounded shape. Curved surfaces, bending space itself in ways that a rope-stretching farmer beside the Nile could never have imagined. And yet those same bending curves are, even now, helping some quiet satellite somewhere overhead know exactly where it sits above the surface of this turning world. You don't need to hold on to any single piece of that. Let the names fall away if they want to. Let the centuries blur together, Egypt folding into Greece, Greece folding into the Islamic world, folding into Renaissance Florence, folding into 19th century mathematicians scribbling in candlelight, folding, finally, into this very room, this very night, this very breath you're taking right now. None of it needs to stay sharp and separate in your mind. It's allowed to soften, the way a coastline softens the less closely you look at it, the way every hard edge in this story has been quietly rounding itself off, sentence by sentence, the further we've gone. If you think for just a moment about how very old this whole story is, 4,000 years and more, stretching all the way back to muddy fields and knotted ropes, there's something almost soothing in that scale. Whatever worries might have followed you into bed tonight, whatever small or large thing was sitting on your chest when you first lay down, it is, in the grand slow sweep of this story, a very brief and passing thing. The triangle didn't rush. The circle didn't rush. Pi took centuries to be gently narrowed down, decimal by patient decimal, and nobody along the way seemed to mind the slowness of it. There's a kind of permission in that, if you're willing to receive it tonight. Permission to be slow. Permission to not have everything solved by morning. Permission to simply rest, the way a shape rests, without needing to prove anything about itself to anyone. Feel, one more time, the shape of the room around you, however dim, however unclear it might be, behind closed eyes. The walls meeting the ceiling in their quiet right angles. The soft curve of whatever you're lying on, holding you the way it has been holding you this entire time, without complaint, without needing anything back from you at all. Somewhere close by, or somewhere further off, other quiet geometric things are simply continuing to be what they are. A honeycomb, holding its efficient hexagons together in the dark. A crystal, somewhere, holding its patient symmetry. A far-off orbit, tracing its slow ellipse overhead, indifferent to the hour, indifferent to whether anyone below is awake to notice it. None of these things are waiting on you. That's the quiet comfort tucked inside all of tonight's long story. Geometry doesn't need witnesses to keep working. The proofs remain true whether or not anyone rehearses them. The shapes hold their form whether or not anyone is there to measure them. And so, in a very real sense, you are free now. Free to stop tracking the thread of the story, free to let your thoughts go loose and untethered, drifting the way a boat drifts once its rope has finally been let go. If a stray thought surfaces, some small fragment about a triangle, or a rope, or a curve stretching gently through space, let it rise and let it pass, the way a single wave rises and falls, without needing to become anything more than that. There's no quiz tonight. There never was. There's only this slow settling, this soft unwinding, this gentle release of whatever you were holding on to when this recording first began. Your breathing has likely slowed already, more than you probably realize. Your body has likely grown heavier against whatever is holding it, the way any shape grows heavier once it stops resisting the space around it. That's not something you need to do. That's simply something that happens, quietly, on its own, the same way pi simply is, the same way a triangle's angles simply add to what they add to, without any effort, without any strain, just because that's the shape of things. So let this be the last thought we leave together tonight, soft and unhurried, the way everything else tonight has been. You are, and have always been, a shape held gently inside a much larger shape, a body resting inside a room resting inside a curve of the earth, a planet resting inside the slow, patient turning of the universe itself. Nothing about that arrangement requires your attention to keep functioning. Nothing about it needs your effort tonight or any night. It simply holds, quietly, the way it always has. Let your eyes stay closed now, if they aren't already. Let your thoughts loosen their last few threads. Let the shapes of this whole long story settle into the background, the way distant hills settle into the horizon at dusk, present, but no longer needing to be looked at directly. There is nothing left to measure, there is nothing left to prove. There is only this, the soft, rounded quiet of a mind letting go, a body settling deeper into rest, a night holding its shape around you, steady and unchanging, for exactly as long as you need it to. Rest now. You don't have to hold anything else tonight. The geometry will keep its quiet, patient shape without you, the way it always has, the way it always will, long after this voice has gone silent, long after this night has folded itself gently into the next. There's a particular kind of quiet that settles into a room Once a long story has finally been told, all the way through, and that's the quiet we're resting in now. Nothing more needs to be added, nothing more needs to be explained. What's left is simply the soft, unhurried work of letting the body catch up to where the mind already is, somewhere calm, somewhere loose, somewhere close to sleep. If you think back, just faintly, to the very beginning of tonight, you were lying there, feeling the curve of the earth pulling you gently down into the mattress, and I told you that you were, in that exact moment, a shape. That hasn't changed. You're still a shape, resting inside a room that is itself a shape, resting on a planet that is a very large, very old, very patient shape, turning quietly through a night sky that has been turning this same slow way for longer than anyone could ever really imagine. Nothing about that arrangement has shifted since we started. If anything, it's settled a little more firmly into place, the way a stone settles a little deeper into soft ground the longer it rests there. Let your body notice that settling now, if it hasn't already. The weight of your legs, resting exactly where they are. The weight of your arms, resting exactly where they are. Nothing needs to move. Nothing needs to adjust. Whatever position you found yourself in by this point in the night is very likely close to the shape your body wants to hold on to as it drifts the rest of the way down into sleep. So there's no need to search for anything better, no need to reposition or reconsider. You've already found your resting shape. Let it be enough. There's something quietly reassuring in the fact that geometry, this enormous, ancient 4,000-year-old story we've spent tonight walking through together, never once needed anyone's permission to be true. The 3-4-5 triangle worked for the rope stretchers along the Nile, whether or not they understood why. The Pythagorean theorem held for every right triangle that ever existed, long before anyone had proven it, and it kept holding true after the proof arrived too, completely unchanged by human attention. Pi sat quietly inside every circle, whether anyone was measuring it or not. None of it needed to be watched over. None of it needed anyone awake and alert to keep it functioning correctly. It simply was, and simply continued being, the same way it will keep being long after tonight has passed into tomorrow, and long after tomorrow has folded itself into all the days that come after. You are allowed that same kind of quiet permission right now. You don't need to stay alert to keep your own breathing going. You don't need to watch over your own heartbeat to make sure it continues. These things too simply are, and simply continue being, the same steady way a triangle continues holding its angles at 180 degrees, whether or not anyone in the room happens to be thinking about triangles. Your body already knows how to rest. It's been practicing this every single night of your life. Tonight is no different, except that maybe, just maybe, it's a little easier than usual, because your mind has spent the last little while walking slowly through something old and steady and calm, rather than circling around whatever it might have been circling before this recording began. If any small worry tries to surface now, right at this final stretch, let it rise the way a single ripple rises on still water, and let it fade the same way, without needing to be chased or examined or solved. There's nothing left to solve tonight. The proofs are finished. The shapes have found their places. Whatever concern might be quietly waiting at the edge of your thoughts can simply wait there, undisturbed, until morning, when you'll have an entirely different set of resources, an entirely different kind of clarity, a whole rested mind, ready to meet it if it still matters by then. Tonight, it doesn't need you. Tonight is only for resting. Picture, one last time, that single point of light we returned to earlier, resting alone, with nothing around it at all. No size, no direction, no worry attached to it whatsoever. Just a quiet location, existing simply because it exists. Let your own awareness soften into something like that now. Small and still, and entirely without edges. The way a point has no edges. The way a point simply rests exactly where it is, needing nothing else from the space around it. And if that point begins to blur, the way points sometimes do at the very edge of sleep, softening into something rounder, something less defined, let it blur. You don't need sharp edges right now. You don't need clean lines or careful definitions or precise angles measured out to the exact degree. All of that belongs to the waking world, to tomorrow, to whenever your mind decides it wants to pick up a pencil again and draw something clean and deliberate onto a page. Tonight, softness is exactly what's needed. Tonight, the blur is the destination, not a mistake to correct. Somewhere above you, whether you can sense it or not, the same patient curve of space that Einstein spent years working to understand is still quietly doing what it has always done, bending gently around everything with enough weight to bend it, including the small, warm, breathing shape of you, resting here in the dark. You don't have to understand the mathematics behind that curve to be held by it. You never did. It was holding you long before tonight's story began, and it will keep holding you long after you've stopped listening altogether, the way it holds everyone, everywhere, all the time, without asking anything in return. Let your thoughts, if there are any left drifting through your mind right now, grow slower and further apart, the way the last few raindrops fall further apart from each other as a storm finally passes. There's no need to catch them. There's no need to follow them anywhere. Just let them fall, quietly, into whatever soft, dark space is waiting to receive them, the same soft, dark space that's waiting, patiently, to receive you. If you're already asleep, then none of these last words matter at all, and that's exactly as it should be. This recording was never really for the waking mind to memorize. It was only ever meant to be a companion for the space between waking and sleeping, something steady to walk alongside while your body did the quiet work of letting go. And if you're still here, still listening, even faintly, even at the very last edges of awareness, know that there's nothing more required of you now. You've done everything this night asked of you, simply by staying still, simply by breathing, simply by letting a very old, very patient story settle over you the way water settles into the shape of whatever it's poured into. The room around you will keep its quiet right angles through the night, the same right angles the Egyptians once found with nothing more than a length of knotted rope. The bed beneath you will keep holding the particular curve your body has settled into without needing to be reminded. And somewhere out past the ceiling, past the roof, past the atmosphere itself, the old, familiar shapes of the night sky will keep tracing their slow, patient paths, indifferent to the hour, indifferent to whether you're awake to watch them, content simply to keep moving the way they always have. There's nothing left to add to that. There's nothing left to explain or prove or measure. Only this last, quiet moment of rest, held gently inside a room, inside a curve, inside a universe that has always been far larger and far more patient than any single night could ever require you to understand. So let this be where we finally stop. No more history, no more shapes to trace, no more centuries to walk through together. Just the soft weight of your own body, settling fully now into whatever rest looks like for you tonight. Just your breath, slower now, quieter now, needing nothing more from this night than to keep going gently until it finally lets go entirely. Rest now. You've carried nothing here that needs to be carried any further. The shapes will keep their places, the way they always have. The night will hold its geometry without you, exactly as long as you need it to, and it will still be holding that same quiet geometry whenever you're ready, tomorrow, or whenever tomorrow finally decides to arrive. Let's slow down now, even further than before, and spend real time with the pieces geometry is actually built from. Not the history anymore, not the names or the centuries, just the shapes themselves, resting quietly underneath everything we've already heard tonight, waiting to be looked at slowly, one at a time. Everything begins with something almost too simple to imagine: a point, a single location in space with no size at all. Not small, not tiny, truly no size whatsoever, just a position and nothing more than that. It sounds like a strange thing to build an entire field of thought around, something with no size, no weight, no shape of its own. But that emptiness is exactly where the power comes from. A point has no messiness to it, no uncertainty about where it sits. It simply is, in one exact place, and nowhere else at all. Now let that point begin to move, stretching out in one direction, and you have a line. A perfectly straight path, reaching forward and backward without ever stopping, made of countless points lined up beside each other with no space between them. A line has length in the sense that it goes on, but it has no width, no thickness, nothing you could actually touch. You have never truly seen a geometric line, and you never will, because any line drawn with a pencil, or a laser, or anything else, always has some small width to it, however thin. The lines we draw are only approximations, stand-ins, quiet gestures towards something that exists only in careful thought, never quite in the physical world around you. If you take just a piece of that endless line, a stretch with a clear beginning and a clear end, you get what's called a line segment. This is probably closer to what comes to mind when you picture drawing a straight line on paper, something with two definite ends, rather than something reaching on forever. And when two line segments meet at a shared point, that meeting point is called a vertex, and the opening between the two segments, the amount of turning from one direction to the other, is what we call an angle. Angles are measured in units called degrees, and a full turn all the way around is divided into 360 of them, an old inheritance passed down from a counting system used long before any of us were born. A right angle, that perfect 90-degree corner we spent time with earlier tonight, is exactly 1/4 of that full turn. An angle smaller than that, one that closes in tightly, is called acute, a word that simply means sharp, because these angles do tend to look sharp and narrow. An angle that opens more widely than 90 degrees, but not so wide that it becomes a straight line, is called obtuse, a word meaning blunt or gentle, because these angles spread out more softly. And an angle of exactly 180 degrees isn't really an angle at all, in the way you'd picture one. It's simply a straight line, two segments pointing in opposite directions from the same shared point, no bend between them at all. From these small pieces, points, lines, angles, we can build our first real shape, and it happens to be the most important one in all of geometry. The triangle. 3 sides, 3 angles, closed into a single, simple, sturdy form. And here is something worth resting on for a moment, something worth hearing more than once tonight, because it deserves to settle in slowly. No matter how a triangle is shaped, no matter how tall or flat or lopsided it becomes, its 3 interior angles will always add up to exactly 180 degrees. Always. A tall, narrow triangle, a wide, low one, a perfectly balanced triangle where every side matches every other side. It makes no difference at all. The 3 angles inside will always sum to that same 180 degrees every single time, without exception. Triangles come in a few familiar families, and it's worth knowing their names, gently, without any pressure to remember them. A triangle with all 3 sides the same length is called equilateral, and its 3 angles end up equal too, each one exactly 60 degrees. A triangle with exactly 2 matching sides is called isosceles, and the 2 angles across from those matching sides turn out to match each other as well. A triangle where every side is a different length is called scalene, and its 3 angles are all different too. And a triangle that contains one perfect 90-degree corner, the kind we spent so much time with earlier tonight through the Egyptian rope and through Pythagoras, is called a right triangle. There's something else worth remembering about triangles, something we touched on earlier, but that deserves to be felt again here, slowly. A triangle is rigid. If you build one out of 3 fixed rods, joined loosely at each corner, that shape cannot bend or shift at all, no matter how hard you push on it. A square, by comparison, can lean sideways into a slanted parallelogram shape, even while its 4 sides stay exactly the same length. But a triangle holds its form. It cannot collapse. This is why you'll find triangular bracing tucked into bridges, into roof beams, into the quiet framework of towers, anywhere a structure needs to resist bending under weight. That steadiness traces all the way back to this one simple fact about triangles, that once the 3 sides are fixed, the whole shape is fixed along with them. From 3 sides we move to 4, and here we find shapes you already live among constantly, even if you've never thought of them in these exact terms. A square has 4 equal sides and 4 right angles, each corner opening to exactly 90 degrees. A rectangle also has 4 right angles, but its sides come in 2 matching pairs rather than 4 identical lengths. Think of a door, or a book resting somewhere nearby, or the screen you may have looked at earlier tonight before setting it aside. A parallelogram has 2 pairs of sides that run in the same direction and never meet, no matter how far they stretch, but its corners aren't locked into right angles the way a rectangle's are. It can lean, gently, like a rectangle pushed sideways. A rhombus has 4 equal sides, much like a square, but its angles can tilt, giving it that familiar diamond shape. And a trapezoid has just 1 pair of sides running parallel to each other, with the remaining 2 sides angling inward or outward on their own. Beyond 4 sides, shapes fall into a broader family called polygons, a word that simply means many angles. 5 sides makes a pentagon, 6 makes a hexagon, 7 a heptagon, 8 an octagon, and when every side of one of these shapes is equal in length and every angle equal too, the shape is called regular. The way a stop sign is a regular octagon. 8 matching sides, 8 matching angles, evenly spaced around a center. There's a quiet pattern hidden in this too, one worth noticing gently. As a regular shape gains more and more sides, its corners soften, its angles stretch closer and closer to a full straight line, and the whole shape begins to look less like a polygon and more like a circle. A circle, in a sense, is simply what happens when a shape has so many tiny sides that the corners disappear entirely. This idea of shapes fitting together leads us naturally into something called tessellation, the fitting of shapes across a flat surface with no gaps left behind and nothing overlapping. You've likely seen this without naming it, in tiled floors, in brick walls, in the honeycomb pattern bees build without ever being taught. Only a few regular shapes can do this fitting together entirely on their own. Triangles can, because 6 of them, each with their 60-degree corners, gather perfectly around a single point, adding up to a full circle's worth of turning. Squares can too, 4 90-degree corners meeting neatly at each junction. And hexagons can as well, 3 of their 120-degree angles closing the gap completely. But a pentagon, oddly, cannot. Its angles never quite divide evenly enough to close the space around a point, always leaving either an awkward sliver of a gap or a slight, stubborn overlap. And running quietly beneath nearly every shape we've mentioned tonight is one more idea: symmetry. A shape carries symmetry whenever there's some way to move it, by flipping it as though in a mirror, by turning it around a center point, or by sliding it along a repeating pattern so that it lands back exactly where it started, indistinguishable from before. A square holds a great deal of symmetry this way. It can be reflected across 4 different lines and turned into 4 different positions, and each time it looks precisely the same as it did before you moved it at all. A shape with an irregular, lopsided outline holds none of this. There's no way to move it and have it land back on itself unchanged. All of this, the point with no size, the lines stretching endlessly in both directions, the angle formed where 2 segments meet, the triangle that refuses to bend, the square and the hexagon fitting so neatly into the world around you, is the quiet architecture beneath everything geometry ever became. Small pieces resting together, patiently, the way small pieces of thought settle together in a mind that's slowly letting go of the day behind it. You don't need to hold on to any of these names right now. They'll still be here later, unchanged, waiting exactly where you left them, the way a triangle waits, rigid and steady, whether or not anyone happens to be looking at it at all. Let's rest here for a while longer and turn our attention to something a little more spacious, something you can almost feel, if you let yourself. Area. How much room a flat shape actually takes up, how much surface it covers. This is one of the oldest and most practical ideas in all of geometry, and it's worth moving through slowly, because it connects all the way back to where we started tonight, with farmers along a river, trying to measure their land after the water pulled back and left everything uncertain again. Picture the simplest possible way to think about area. A small square just 1 unit long on each side. Not large, not small, just one small unit, sitting there as a kind of measuring block. And the area of any shape at all is really just asking a quiet question. How many of these small unit squares would it take to cover this shape completely, with nothing left uncovered and nothing overlapping? That's all area ever really is. A count of small squares, fitted together until a larger shape is filled. For a rectangle, this is fairly easy to feel. Imagine a rectangle that stretches 4 units across and 3 units down. You could lay out those small unit squares in neat rows, 3 rows of 4 each, or 4 rows of 3, either way arriving at 12 small squares in total. And that's exactly why the area of a rectangle is found by multiplying its length by its width. Length times width, 4 times 3, 12. Simple and steady, and something you can picture clearly even with your eyes closed. Rows of small squares settling quietly into place. A triangle asks for a slightly gentler kind of imagining. Picture any triangle at all, resting in front of you. Now picture a second triangle, an exact copy of the first, flipped upside down, and slid up against the first one along one of its sides. Something pleasant happens when you do this. The 2 triangles together form a parallelogram, a 4-sided shape whose area you already know how to find, its base multiplied by its height. And since your triangle is exactly half of that combined parallelogram, its own area must be exactly half as well. 1/2 of the base, multiplied by the height. That's the whole idea, held gently in one simple picture. 2 matching triangles, leaning against each other, quietly forming a shape you already understood. A circle asks for something different again, because a circle has no straight edges to measure along, no rows of little squares that fit neatly into its curve. This is where that old number, pi, returns to us, the same number Archimedes spent so much careful effort narrowing down using his many-sided polygons, centuries and centuries ago. The area of a circle comes from pi, multiplied by the radius and then multiplied by itself once more. And here's a soft way to feel why that's true, rather than simply accepting it as a rule to memorize. Imagine slicing a circle the way you might slice a pizza, into many thin wedges, so many wedges that each one is almost impossibly narrow. Now imagine laying those wedges down side by side, alternating one pointing up, the next pointing down, fitting together edge to edge. What forms, once you have enough of these thin slices, starts to look almost exactly like a rectangle. Not quite, but closer and closer, the thinner your slices become. That near rectangle has a height equal to the circle's radius, and a width equal to half of the circle's distance around. Multiply those 2 together, the way you would with any rectangle, and you land, quietly, on pi times the radius, multiplied by itself. The same gentle squeezing Archimedes once used with his polygons. Curved shapes eased, patiently, into something straight-edged enough to measure. Now let's lift ourselves, softly, out of flat shapes altogether, and into the fuller, rounder world of 3 dimensions. Because up until now, we've mostly been speaking about drawings, flat things resting on a page. But the room around you tonight is not flat. It has depth. It has height, it has length, and geometry, once it steps into 3 dimensions, stops talking about area and starts talking about volume, how much space something actually takes up, how much water it could hold if it were hollow, how much material it would need if it were solid all the way through. A cube is the simplest of these 3-dimensional shapes, built from 6 matching squares, and its volume comes from multiplying its length, its width, and its height together. And because all 3 of those measurements are the same in a cube, this becomes simply the side length, multiplied by itself, and then multiplied by itself once more. A rectangular box works in much the same gentle way, length times width times height, even when those 3 measurements differ from one another, the way a shoebox is longer than it is tall, and taller than it is deep. A cylinder, something shaped like a can, finds its volume by first finding the area of its circular base. That same pi times radius we just walked through together, and then stretching that flat circular area upward through the cylinder's full height, as though stacking flat circles, one atop another, all the way to the top. And a sphere, a perfectly round ball, holds its volume in a formula Archimedes himself worked out, long ago, through that lovely relationship between a sphere and the cylinder that snugly contains it. 4/3 multiplied by pi, multiplied by the radius, 3 times over. There's a kind of quiet comfort in noticing how these formulas echo each other. Area asks a flat question: how much surface does something cover? Volume asks a fuller, rounder question: how much room does something actually take up in the world? And each one builds gently from the last, area growing out of length and width, volume growing out of area, and one more added dimension, height or depth, stacking upward, filling out, becoming something you could hold in 2 hands, rather than something you could only look at on a page. Let's turn now, gently, to one more idea, something related to shapes matching each other, though in a softer, more flexible way than the exact matching we spoke of earlier tonight. 2 shapes are congruent, remember, when they are exactly identical, the same size, the same form, down to every last measurement. But 2 shapes can also be similar, which means something a little different and a little more forgiving. Similar shapes share the very same form, the very same proportions, but not necessarily the same size. Think of a photograph and a larger print made from that same photograph. Every detail matches, every angle stays the same, but the whole image has simply grown or shrunk evenly in every direction at once. Every angle in one shape matches its counterpart in the other exactly, and every length in one shape has been scaled by the very same amount throughout. Nothing stretched more in one direction than another, nothing pulled out of its original proportion. This idea of similarity turns out to hold a quiet kind of power, more than it might seem to at first. It's the very idea, in fact, that let Thales measure the height of a pyramid he could never have climbed, simply by watching his own shadow stretch across the sand. His own small shape, his body and its shadow, formed a triangle that shared the very same proportions as the far larger triangle formed by the pyramid and its own long shadow. Because those 2 triangles were similar, sharing the same shape even at wildly different sizes, the ratio he could measure easily in his own small shadow told him, with total certainty, the ratio hidden inside the enormous, unmeasurable one beside it. This same gentle principle, using something small and easily known to reveal something large and otherwise out of reach, echoes quietly through so much of the practical geometry that surrounds you, even now. A map is similar to the vast landscape it represents. Every road and river shrunk down by the very same amount, so that the small shape in your hands still tells the truth about the enormous shape it stands in for. An architect's small model of a building holds the very same relationship to the finished structure that will eventually rise up around it, every wall and window scaled down evenly, nothing distorted, nothing out of place. Even a photograph, enlarged or shrunk to fit a frame, keeps faith with the scene it once captured, because its proportions were never allowed to drift. There's something worth resting on here, before we move any further into tonight. Area and volume and similarity, each one, in its own quiet way, is about relationship. Area relates a shape to the space it fills. Volume relates a shape to the room it occupies in 3 full dimensions. And similarity relates one shape to another, entirely different shape, tying them together not by size, but by form, by proportion, by the deeper pattern that stays the same, even as everything else changes around it. This is, in a sense, what geometry has always been reaching for, underneath all its centuries of history. Not simply naming shapes, but understanding how they relate to each other, how a small triangle can tell you the truth about an enormous one, how a handful of narrow wedges can gently become a circle, how a cube and a cylinder and a sphere, each so different from the others, still share the same quiet, underlying logic of length and width and depth, folding together into something whole. You don't need to hold on to any particular number tonight. Not pi, not the formula for a sphere, not the ratio hidden inside a photograph. What matters, if anything matters at all right now, is simply the feeling underneath these ideas, the sense that shapes fit together, that small things can quietly explain large things, that even something as vast and curved as the world outside your window follows the very same patient, steady logic as a small triangle drawn once, long ago, in the sand beside a pyramid. Let that feeling settle now, the way water settles into whatever shape happens to hold it. There's nothing left to solve tonight, only shapes resting quietly in their places, exactly as they were always meant to. Let's rest here a while and turn our attention to something quieter than a formula, a single sentence, one that a very old book asked its readers to simply accept, without proof, because it seemed too obvious to need one. And yet that one sentence, sitting almost unnoticed near the back of a much larger list, ended up taking over 2,000 years to fully understand. You'll remember, from earlier tonight, that Euclid built his entire system on a small handful of starting points, things so plain and so self-evident that no one felt the need to argue with them. A straight line can be drawn between any 2 points. A straight line can be stretched out forever, longer and longer, without limit. A circle can be drawn around any center at any distance you like. All right angles match each other exactly. 4 short, quiet statements, each one so obviously true that nobody who read them ever felt any need to push back. Then came a 5th, longer than the others, a little more tangled in its wording, and it said, in its simplest possible telling, something like this: if you have a straight line and a point somewhere off to the side of that line, there is exactly one other line you could draw through that point that would run alongside the first line forever, never touching it, no matter how far both lines were stretched out in either direction. Picture that for a moment, gently, the way you might picture 2 roads running side by side into the distance. One road below, one point resting somewhere above it, and just one single road you could draw through that point that would run alongside the first, forever, always the same distance apart, always missing it by exactly the same small margin, mile after mile, without limit. That feels obviously true. Of course there's only one such line. What else could there possibly be? And for a very long time, nearly everyone who read Euclid's work felt exactly that same quiet certainty. But underneath that certainty, a small unease kept returning, generation after generation, in reader after reader, across many different centuries and many different corners of the world. Something about this 5th statement didn't sit quite as easily as the other 4. It felt less like a simple starting point, and more like something that ought to be provable, something that should follow naturally from the earlier 4, rather than needing to be assumed all on its own. So mathematician after mathematician, working across Greek scholarship and later Islamic scholarship, and later still European scholarship, tried, patiently, to prove that this 5th statement wasn't really a separate assumption at all. They tried to show that it could be derived, logically, step by step, from the 4 simpler statements that came before it, the way so many other truths in geometry had already been derived. Every one of these attempts, across more than 2,000 years, quietly failed, not because the people trying were careless or unskilled. Some of the sharpest minds in the history of mathematics spent real years of their lives on this single sentence, and every one of them, eventually, had to set it down unfinished. There's something worth sitting with in that. 2,000 years is an extraordinarily long stretch of human effort to spend on one sentence. Longer than most civilizations have lasted, longer than most languages have existed in their current form. And yet this single, quiet unease about parallel lines simply refused to resolve itself, refused to be proven, and refused, just as stubbornly, to be disproven either. Then, in the early 1800s, a small handful of mathematicians, working mostly apart from each other, in different countries, without knowing what the others were doing, tried something different. Instead of continuing that long effort to prove the 5th statement was true, they asked a much stranger question. What would happen if it simply wasn't? What would happen if you assumed, just for the sake of following the logic wherever it led, that there could be more than one parallel line through that point? Or, in another version, that there could be no parallel line at all, Most people, faced with a question like that, would expect it to collapse quickly into nonsense, a contradiction, some obviously broken result that would prove, in a roundabout way, that the original statement really did have to be true after all. That's what nearly everyone assumed would happen, but it didn't happen. What these mathematicians found instead, slowly, carefully, was that you could build an entirely new and internally consistent geometry on top of this different assumption, a geometry every bit as logical and complete as Euclid's own, just built on a different foundation. To feel your way into how that's even possible, it helps to stop thinking about flat surfaces for a moment and picture something curved instead. Picture the shape of a saddle, the kind you might rest on a horse's back, curving upward on two sides and downward on the other two. On a surface shaped like that, lines that would have stayed perfectly parallel on a flat table start to drift apart from each other as they travel, spreading gently wider the farther they go. On a surface like this, you actually can draw more than one line through a single point that never crosses a given line, several of them, all following the shortest possible path between their own two ends, which is really what a straight line comes to mean, once you're standing on a curved surface rather than a flat one. Not something perfectly straight in the old sense, but simply the shortest way from one place to another, wherever the surface happens to bend. Now picture the opposite kind of curve, a sphere, like the surface of the Earth itself, the one holding you right now as you rest. On a sphere, there's no such thing as a parallel line at all, not in the way Euclid meant it. Every great circle drawn around a sphere, the kind that cuts it exactly in half, will always eventually cross any other great circle, no matter how carefully you try to keep them apart. Think of two lines of longitude, starting out side by side at the equator, seeming, for a while, as though they'll run alongside each other forever. But follow them upward, toward the pole, and you'll find them drawing closer and closer until they finally meet, exactly at the top. What looked like two parallel lines were quietly converging the entire time, simply because the surface beneath them was curved rather than flat. And something else changes too on a surface like this, something we touched on gently before. On a flat surface, the three angles inside any triangle always add up to exactly 180 degrees, without exception. But on a sphere, that quiet rule loosens and bends along with everything else. A triangle drawn on the curved surface of a sphere can hold more than 180 degrees inside it, sometimes considerably more, depending on how large the triangle is and how much of the sphere's curve it happens to wrap around. The very same shape, the very same three straight sides meeting at three corners, behaves differently depending on whether it's resting on something flat or something curved. This whole family of alternative geometries came to be known as non-Euclidean geometry, and for a long while after it was first worked out, it remained little more than an elegant curiosity, tucked away inside mathematics, admired for its internal consistency, but seemingly disconnected from anything in the physical world outside. Nobody who developed these curved geometries in the early 1800s was trying to describe anything real. They were simply following a single stubborn assumption to see where it might lead, purely as an exercise in careful reasoning. And yet, roughly a century later, this same abstract, seemingly useless curiosity turned out to be exactly the mathematical language needed to describe how gravity actually behaves in the real universe. The very language Einstein would eventually reach for, to explain why massive objects bend the space around them, and why falling is really just following the straightest possible path through a world that is no longer flat. Let's rest a little longer now, and turn back to something gentler, something we've mentioned a few times tonight already, but haven't yet spent real, quiet time with: the circle. One of the simplest shapes there is, and also one of the deepest. A circle is, at its heart, nothing more than every single point that sits at exactly the same distance from one fixed center. That's the whole definition, held in one soft sentence. A center and a constant distance stretching out from it in every direction at once, tracing a perfectly even curve all the way around. That constant distance, from the center out to the edge, is called the radius. And if you draw a straight line all the way across the circle, passing directly through the center and touching the edge on both sides. That full stretch is called the diameter, always exactly twice the length of the radius, since it's simply two radius lengths laid end to end. The distance all the way around the outside of the circle, if you traced your finger along its curved edge and came back to where you started, is called the circumference. And here, quietly, is where that old number pi returns to us one more time. The circumference of any circle at all, no matter how large or how small, is always exactly pi multiplied by the diameter. Always. A circle the size of a coin and a circle the size of a planet both hold this very same ratio inside them, unwavering, unchanging, true across every possible size a circle could ever take. There's something worth sitting with in that stillness. Pi wasn't chosen by anyone. It wasn't agreed upon the way 60 minutes in an hour was once agreed upon, long ago, by people counting in a different base than we do today. Pi is simply there, folded into the very shape of a circle, waiting quietly to be found, rather than invented. A number that never repeats and never quite ends, no matter how far you follow its digits. And one more soft circle fact, before we let this section go, one that reaches all the way back to Thales, the very first person we spoke of tonight who tried to move geometry from simple trick towards something proven. Picture a circle and a diameter drawn straight across it. Now choose any third point, anywhere at all along the remaining curve, and draw two lines from that point back to each end of the diameter. What forms, every single time, no matter where along the circle you choose that third point, is a perfect right angle. Always 90 degrees, without exception, held steady by the shape of the circle itself. A small, quiet rule, tucked inside the simplest shape there is, waiting patiently for anyone who takes the time to notice it. Let all of this settle now, gently, without needing to be held too tightly. A sentence about parallel lines, unresolved for 2,000 years. A curve that bends, and a rule that bends along with it. A circle, holding its center, its radius, its quiet constant ratio, exactly the same tonight as it was 4,000 years ago, and exactly the same as it will be tomorrow, whether you remember any of it or not. Let's stay a little longer with circles, because there's one more small, quiet idea worth resting on before we move forward into new territory tonight. It has to do with tangent lines. Those lines we touched on earlier that reach out and touch a circle at exactly one single point and then continue on their way without ever crossing into the circle's interior. Picture a straight line drifting past a circle close enough to just barely brush its edge at one single spot and no other. That's a tangent line. It doesn't cut through. It doesn't clip a small piece off the side. It simply grazes the circle once and moves on. Here's the small, steady fact hidden inside that touch. Wherever a tangent line meets a circle, it always meets the circle's radius, drawn out to that exact point of contact, at a perfect right angle, every single time. For every circle, and every tangent line that has ever been drawn, or ever will be. There's no exception to this, no special case where the angle drifts even slightly away from 90 degrees. The touch is always perpendicular, always square, always locked into that same quiet right angle, no matter how large the circle, no matter where along its edge the tangent happens to land. This small rule turns out to be quietly at work in a great many ordinary moments. Think of a stone, tied to the end of a string, spun around and around in a circle and then released. The instant that string lets go, the stone doesn't keep curving. It flies off in a straight line, and that straight line is a tangent to the circular path it had just been following, meeting the radius, at that exact moment of release, at a perfect right angle. A spark thrown off a spinning grinding wheel behaves the very same way. So does a bit of mud flung from a bicycle tire. All of these small, everyday motions are quietly obeying a rule about circles and tangent lines that was worked out, carefully and patiently, a very long time ago, by people who were simply curious about shapes, with no thought at all towards spinning wheels or bicycle tires. Let's move now into something a little different, A shift that changed the whole character of geometry, centuries after Euclid and Archimedes, and all the careful straight-edge and compass work that came before it. This shift arrived through a man named René Descartes, a French philosopher and mathematician working in the early 1600s. And the idea he brought forward is one you may have already met, without quite realizing how old and how significant it actually is. Descartes had a realization that sounds simple once it's explained, though it took real imagination to arrive at in the first place. He proposed that you could describe the exact location of any point on a flat surface using nothing more than two numbers. One number telling you how far to move sideways, left or right, from some fixed starting spot, and a second number telling you how far to move up or down from that very same spot. Two simple numbers, and suddenly, any point at all, anywhere on a flat page, could be pinned down exactly, with no ambiguity at all. You may recognize this as the coordinate grid, the familiar horizontal and vertical numbers you likely encountered long ago in school, still carrying Descartes' own name today. Cartesian coordinates, a quiet echo of one mathematician's idea, still living on, centuries later, every time a graph is drawn. What Descartes understood, and what made this idea so quietly powerful, was that once every point could be described with numbers, entire shapes could be described with numbers too. Not drawn, not constructed with a straight edge and a compass, the way the ancient Greeks had always insisted, but written, instead, as an equation. A circle, that same familiar shape we've spent so much time with tonight, that set of points sitting at exactly the same distance from a center, can be captured in a single, tidy algebraic statement, connecting those two coordinate numbers together. A straight line can be written even more simply still. And once a shape exists as an equation rather than only as a drawing, an entirely new set of tools becomes available. You can use the methods of algebra, the careful, step-by-step manipulation of numbers and symbols, to answer questions about shape, without ever picking up a compass, without ever drawing a single line by hand. This fusion of algebra and geometry earned itself a name, analytic geometry, sometimes called coordinate geometry, and it represents a genuinely new way of thinking about shape. Not something you build, the way Euclid always insisted, with physical tools and careful construction, but something you can describe and adjust and reason about purely through numbers, sitting quietly on a page, or, many centuries later, glowing quietly on a screen. This shift turned out to open doors that had stayed firmly shut for the ancient Greeks, no matter how clever or how patient they had been. Some geometric problems that were extremely difficult or even flatly impossible to solve using only a straight edge and a compass became solvable almost effortlessly once translated into the language of algebra instead. And it opened the door, too, to describing curves far stranger and far more intricate than anything the Greeks had ever systematically studied. Curves that couldn't easily be drawn with simple tools, but that could be written, cleanly, as equations. A few decades later, this same fusion of algebra and geometry helped set the stage for an entirely new field, calculus, developed independently by Isaac Newton and Gottfried Leibniz in the second half of the 1600s. A field built almost entirely on the idea of studying how things change, moment to moment, point by point, something that becomes far easier to study once a curve exists as an equation, rather than only as a drawing on a page. Closely tied to this same coordinate way of thinking, though reaching back further into history, with roots in ancient Greek and Indian and Islamic mathematics as well, is a field called trigonometry. The word itself simply means triangle measurement, and that's exactly what it sets out to do, carefully describing the relationships between the angles of a triangle and the lengths of its sides, particularly for right triangles, the same kind we spent so much gentle time with earlier tonight. Trigonometry introduces three simple ratios, given the names sine, cosine, and tangent, each one describing a steady, dependable relationship between a right triangle's angles and the proportions of its sides. And here's the quietly remarkable part, worth repeating slowly, because it echoes something we already spent time with tonight. These ratios stay exactly the same regardless of how large or small the actual triangle happens to be, so long as its angles remain unchanged. A tiny triangle and an enormous one, sharing the very same angles, will always share these very same ratios too, an idea that ties directly back to similarity, that gentle principle we rested with earlier, where small, known shapes can quietly reveal the truth about far larger, unmeasurable ones. These trigonometric ratios reach far beyond triangles themselves, though, and this is worth sitting with for a moment, because it's a lovely, quiet extension of an old idea into new territory. Any point moving steadily around the edge of a circle traces out a path that can be described using these very same sine and cosine relationships, first worked out for triangles, of all things. And because of this, trigonometry became the natural language for describing anything that oscillates, anything that rises and falls, and rises again, in a smooth, repeating wave. Sound waves, moving through the air around you right now. Light waves, traveling from a distant star. The gentle vibration of a guitar string, settling after being plucked. Even the quiet, alternating hum of electric current running through the walls of the room you're resting in tonight. All of it, in some hidden mathematical sense, traces back to triangles and to a set of ratios first worked out by people trying to measure the height of buildings and the distance to stars, using nothing more than careful reasoning about angles. The ancient Greek astronomer Hipparchus, working around 150 BCE, is often credited with building some of the earliest trigonometric tables, developed specifically to help predict where stars and planets would appear in the sky. Later, Indian mathematicians, including Aryabhata, working around 500 CE, refined these ideas further. And later still, scholars working during the Islamic Golden Age, in cities like Baghdad, carried this same thread forward, translating and expanding on both Greek and Indian sources, before this long inheritance of careful angle measurement eventually made its way into medieval and Renaissance Europe, where it would sit quietly waiting, for a few more centuries, until Descartes came along and gave triangles and circles alike a whole new language to be described in, the language of coordinates and numbers and equations. There's something gentle worth noticing, here, in how these two ideas rest beside each other. Descartes gave geometry a new way to speak, turning shapes into numbers, and numbers into shapes, a fusion that let ancient problems finally be solved, and new problems be imagined for the very first time. And trigonometry, reaching back even further into the past, gave a single triangle's quiet relationships a reach far beyond anything its original discoverers could have imagined, stretching outward into sound, and light, and the slow, steady vibration of nearly everything around you tonight. Two different threads, woven from very different centuries and very different corners of the world, both eventually settling into the same soft, dependable structure, numbers describing shape, and shape describing the world. You don't need to hold on to any particular equation tonight, or any particular ratio. What matters, if anything does, is simply the quiet, patient thread running through all of it. A tangent line touching a circle, always at that same steady right angle. A point on a page, pinned down by nothing more than two simple numbers. A triangle's ratios, echoing outward into every wave that has ever moved through the air. Let it all settle now, the way a wave settles back into stillness once it has finished rippling outward, the way a point rests quietly at its own exact location, needing nothing more than to simply be there.